analyze and process NMR spectral. In addition to creating the platform of knowledge and networking, this webinar also shares the analysis services available in i-CRIM Lab. Upon completing this webinar, participants will be able to integrate and apply the knowledge, and it will be helpful in improving the quality of research and publication. Now, I will brief everyone with some housekeeping rules for our webinar today. Please mute your speaker and video during the webinar. Please use the chat box for Q&A, question and answer session. You will be entertained later. Please fill up the feedback form in the end of webinar. Slides will be emailed after completing the feedback form. Inshallah, I will read all questions during the Q&A session. And before the seminar ends, I would like to invite all participants to switch on the camera for a photography session. Now, I would like to introduce our honorable speaker of the day, Dr. Teh Chin Ho. Let me read some of his brief background. Dr. Teh Chin Ho obtained his PhD in pharmaceutical chemistry from University of Science Malaysia. He joined Broker Malaysia as NMR application scientist in year 2011. He supports Southeast Asia regions and provides the assistance to customers, especially who are new in the natural products plant metabolomics field. His expertise is with different latest software solutions, both for pure compound and mixture, to drive many possible NMR applications into the easier and better. His current area of research is in NMR application that includes metabolomics, quantitative NMR, and fast NMR technique. Without further ado, I would like to welcome Dr. Teh to give his lecture. Dr. Teh, the floor is yours.
Okay, thank you very much, Dr. Nurkhalida. So I will start to share my screen. So can you see my screen?
Yes, Dr. Teh, but it's not in slideshow mode. All right, yes.
Okay. Yeah,
yeah.
Okay. Thank you. Okay, so good morning to everyone. So I would like to thank the organizing committee inviting me to give the talk for this morning. Okay, so let us go through a little bit. So today I will cover some of the main topics. So as shown here, yeah. Okay, so I will start with the basic NMR spectroscopy, and then I will move on to the NMR spectra 1D and the 2D processings, and then later on I will after the Q&A and we have the break, and then after that we come back with the second part, which is the NMR spectral analysis, and we'll follow up with another sessions of the Q&A. So you are welcome to post your questions in the chat. So we will try to answer as much as possible. Yeah, the questions. Yeah. Okay, so let us move on to the basic NMR spectroscopy. So first, what we want to know is what is the NMR. So the acronym of NMR stands for nuclear magnetic resonance. So there are three main components that form the spectroscopy. So first is the target, okay, which is we call the nuclear, and then the magnetic is the measurement conditions that related to the NMR spectrometer. And then the resonance is a phenomenon that we detect during this the sample or during this target within or sit inside the magnetic environment. So when you look into the molecular spectroscopy as a broader aspect, so actually there are many technology that belongs to the under this molecular spectroscopy, and NMR is one of it. So under this molecular spectroscopy, the common thing is that they are using the electromagnetic radiations to interact with the sample. So NMR is also one of the technology that using the electromagnetic radiations that interact with the sample. So then we are going to see how about the NMR spectrometer in general. So at the NMR spectrometer, so when you say the NMR spectrometer, we say the high field, okay, yeah, high field system. So we also have the low field spectrometer. So for the high field NMR spectrometer, so there's the first one is the computer that connected to the spectrometer, and there's the components called the electronic console that is mainly the cable or the electronic parts, okay, that generate the energy for the NMR experiment. And we have one very special component, yeah. So this is we call the superconducting magnet. So usually these magnets make the NMR looks very different from other spectroscopy technique or the instruments. And beside this the superconducting magnet, so there is another important part that form the spectrometer is the NMR probes. So this NMR probe actually is insert from the base of the magnet. So this is the device of the probe that can be put in to the magnet. So this is a short video to show that how this magnet, superconducting magnet related to the probe. So this is a probe. So usually the probe can be inserted from the bottom of the magnet and go into the magnet. Yeah. So this is how the probe and the superconducting magnet. Then we take a look at the NMR sample. So the NMR sample can be solid, can be liquid, okay? So in most of the applications, so we cannot say everything, but most of the applications, the sample usually need to be dissolved, okay? So it means that we are measuring the sample in the solutions. Of course, there is another configurations that you can measure the solid sample. Yeah, so if you have the solid sample, you can also pack the solid sample, but this you need another configuration. And another configurations that is you can measure also the soft tissue, okay? Yeah, so like for example, the biopsy tissue. So those are the options, okay, that you need the special accessory. So for the standard NMR configuration, so usually the sample is dissolved in the liquid form. So you need the NMR solvent to dissolve your sample. And usually this NMR solvent is the deuterated solvent. So you can have different types of deuterated solvent. So the purpose is to dissolve the sample into the solutions. So after this is the dissolved, okay, so then we try to prepare everything into the tubes, okay, yeah. So this is the final picture, okay, yeah. But you will go through some steps. So depends on the sample, yeah. So as already mentioned, so in NMR sample preparations, so usually you need a deuterated solvent for the measurement. Of course, you can also run your NMR without deuterated solvent. So we call it the no-D NMR. So there's a difference between the deuterated solvent measurements and the non-deuterated measurement. Yeah. So, but in most of the time, we are dissolve our sample in the deuterated solvent, okay, to make the experiment easier, okay, and this is more reliable especially when you measure at a long period of time. Yeah. So for the sample preparation, so after you dissolve the sample, so sometimes the sample is not homogeneous. So sometimes you may need to filter the sample. Okay, so let's say you can filter through the 0.45 membrane filter with the syringe, or you can also vortex, okay, or sonicates or centrifuge, so that you can try to get the homogeneous sample, yeah, okay, for the preparations. So after this is done, okay, yeah, so you get the clear supernatants, then you can transfer this amount into the NMR tubes. Okay, so this is the NMR tubes, empty NMR tubes. So usually the tubes can come with the different diameter. So this diameter is also depends on your NMR configurations. So for UKM, so you are using the 5mm probe. So it means that you can use your NMR system to measure your sample that dissolve in 5mm tubes. And of course, okay, you can also dissolve your sample in 3mm. That is your common practice in UKM as well. Yeah, so that is also possible. So there's two options, okay, for the NMR tubes for your configurations. Then after the sample is transferred into the tubes, then we are going to before you can put the sample in, so we're going to insert this sample into one of the special device we call the spinner. Yeah, so the blue spinner is for the room temperature measurement, and for the ceramic spinner, which is in white color, so this is for the elevated temperature. So usually if you need to heat up the sample at more than 100 degrees Celsius, usually more than 90 degrees Celsius, so usually we will recommend you are using you to use the ceramic spinner. So we insert the sample into the spinner, and then we use the sample gauge as this is the look like here. This is the plastic, okay, that they come with some kind of mark. So this sample will insert, and then we can adjust the tubes, okay, so that we have the cover this active window as shown here. So there's a window here. So this is we call the active window, okay, that's correspond to your NMR probe. So after we insert into this sample gauge, okay, then with the sample spinner that hold the sample tubes, then we can load the sample from the top, okay. Yeah, so the sample can introduce into the magnet from the top, okay. Yeah, so then when you go into the top, so you go into the center of the magnet, and then more precisely is go inside the tube, the probes, and in the probes, so you will see that the probe contains some kind of metals, okay. So these are the NMR coil, okay, or the radio frequency coil that is linked or you call the molded to the NMR probes, okay. So the NMR sample will be sitting here, and then there will be the electromagnetic wave that interact between this NMR coil, which is the wire, with the sample that present in the tubes. Okay, yeah. So just this is the important the basic knowledge. Okay, so the NMR measurements will take place when the sample is sitting inside the magnetic environment. So under this magnetic environment, so we are going to carry out a series of NMR experiment. So it means that the NMR measurement will take place when the sample is sitting within this magnetic environment. And when you try to look further, so what are the things that we are going to see, okay, or we're going to detect from this NMR machine or the NMR spectrometer? So we try to look for the NMR targets, okay? So means that what kind of components that able to give us the NMR signal, okay? Yeah. So if you look it through the textbook or any table, so you'll see that there is the particularly related to the NMR. So there is the table that compile all the NMR active nuclei. So as you can see here, all these are the nuclei, okay, with some kind of properties, okay. So we call the spin. So these are the properties that belongs to the particular nuclei. So when we have this table, okay, so we will see this nuclei. So we say that all these nuclei, okay, yeah, they are NMR active, okay, they are NMR active. So why they are NMR active? Because the spins is not zero, okay. The spin here, as I show here, is not zero. So as long as the spin is not zero, they are NMR active, means that they are NMR detectable. So when you take a further look, okay, yeah, so this is the table, the periodic table. So which elements, or we call which isotopes, they are NMR active or NMR sensitive, okay? So these elements that highlighted in the gray in color, they are non-detectable by NMR because the spin quantum number, as I already mentioned, spin have to be not zero. So if these are spin zero isotopes, okay, then they are non-detectable. So we also have groups of isotopes that is not zero. So in this case, not zero. So for example, we take the spin half. So this spin half is critical because usually the spin half isotopes from, for example, all these labeled in green, they are NMR sensitive and they are NMR favorable. So we will prefer to detect this nuclide because this spin half nuclide usually give us a very sharp and narrow line and easy to observe. So this is we call the easy nuclide, okay, with the spin half. So all these are the easy nuclide. So of course, we know that in the natural distribution, so we also have some isotopes, okay? Yeah, we also have the different types of isotopes for the same element. So this element, if they have the spin quantum number more than half, okay, yeah, then we say that these are the more challenging nuclide, okay, yeah. So they are detectable, but because they usually they'll give us the broad line, okay, broad line. So it means that you need the more sensitive instrument or you need the higher concentrations. Okay, so usually for the spin more than half nuclide, so we say these are more challenging. Okay, more challenging compared to the spin half. So this spin quantum number is one property that we can conclude. Okay, yeah. So for the NMR active nuclide. So another way that we can view this NMR active nuclide, okay, with this another special property called the gyromagnetic ratio. So this is another way that we can say that the NMR active nuclide. So as long as the isotopes with this gyromagnetic ratio, then we say that they are NMR active. So it means that not all the nuclide with this gyromagnetic ratio. So this is the gyromagnetic ratio or the magnetogyric ratio is a property that associated with the NMR active nuclide. So with this gyromagnetic ratio, so we say the nuclide, they have or they possess the magnetic property. So only those nuclide with the gyromagnetic ratio, they have this magnetic property, means that they behave like a tiny magnet. So you imagine that in the NMR spectrometer, we have the giant superconducting magnet. So we have the sample sitting within this big magnetic environment. And now the sample also contains the tiny magnet. So this tiny magnet from the sample definitely can be interact with the main superconducting magnet, which is our main magnetic field. Yeah. So these interactions will cause the signal to be detected. Okay, so that's why you need a superconducting magnet to be there so that you can observe the magnetic property of your NMR nuclide. Yeah. So when the sample is sitting inside, so we say the sample contains or they possess the gyromagnetic ratio, or we say the gamma. Okay, so gamma is the symbol for the NMR active nuclide. So different nuclide, they have the different gamma. Okay, yeah, different nuclide, they have the different gamma. So and when you look into the NMR sample, okay, so we dissolve our sample into the NMR solvent. And in the sample, we are not just detect one atom, okay? We detect many atoms, millions of atoms. And these atoms, usually they are not hanging, they are not isolated. So usually these atoms can always bonded, okay? So when they are bonded, so we will see the difference, okay? When they bonded, we will see the effect of this bonding. But just take note, okay? Yeah. So we are looking at the not just single nucleus, but we are looking at the millions of nuclei within the tiny NMR tube, 5 millimeter or 3 millimeter. Okay. So the next question is, what are the three most favorite nuclei in NMR spectroscopy? Okay, so we know that the spin half nuclei, okay, there are a number of spin half nuclei. So we say if you want to make some ranking, okay, so which is the top three, okay, nuclei, okay, in the NMR world. So usually we look for the nuclei which are spin half and then they are sensitive, okay. Yeah, not just spin half, but they are sensitive. So how can we rate the sensitivity? So the sensitivity can be due to the nuclide itself. So yeah, so which is the gyromagnetic ratio, and the sensitivity also can be related to the natural abundance. Okay, closely related to the natural abundance. So if you look, okay, yeah, so here we have three important isotopes which are very famous in NMR, okay, yeah. So first is the 1H. So this is from the element hydrogen. So element hydrogen, there are three isotopes. So the NMR detect the proton, okay, proton. Why? Because this proton is the most sensitive nuclide in the NMR world. Okay, so the reason is because the natural abundance is high. Okay, the natural abundance is high, it's about 99.98%, and the magnetic ratio is also very high. Okay, yeah, compared to the rest. Okay, so the hydrogens, or we call the protons, is the most sensitive nuclide in the NMR spectroscopy. So the second nuclide is the carbon-13. So we know that these protons, okay, yeah, in the natural group or the natural products, is very often that this proton is covalently bonded to the carbon. Okay, so carbon is the important component or important element in the organic molecule or in the natural products. So among these carbon elements, we have the carbon isotope carbon 12, carbon 13, carbon 14, if you still can recall your high school chemistry. So the carbon 13 is the one of the isotopes that is detectable by NMR spectroscopy. However, okay, yeah, this carbon 13, with this natural abundance, which is quite low, 1.1%. Okay, yeah, but again, this carbon 13 is still the favorite nuclide in NMR spectroscopy. So the third common nuclide, okay, in NMR world is the nitrogen 15. Okay, yeah. So this nitrogen 15 is the important element that presents in the protein. Okay, yeah, protein. Yeah. So that's why there's a favorite focus on this nitrogen 15. Again, the natural abundance is also pretty low, and with the magnetic ratio is also much lower compared to the carbon and the proton. Yeah. So then we look at the NMR result. Okay, yeah. When you place the NMR sample, okay, into the tube, then you measure this with your NMR spectrometer. So what you obtain? So you are getting a number of spectra. Okay, so this spectra could be a 1D, it could be a 2D. Okay, yeah. So all these are the NMR result. Okay, NMR result. So when you look into the NMR result, so we are looking at the fingerprint. Okay, yeah, fingerprint. So if you have the molecule that you put into the NMR magnet, so what you get, okay, you are getting a spectrum, okay, with this fingerprint. So this fingerprint is what we call the chemical fingerprint or biochemical fingerprint. And this fingerprint is highly compound specific. So it means that if you are measuring a molecule, so if you change some kind of the side change, so you will get the different, you're getting the different fingerprint for your NMR measurement or the NMR result. And this is very powerful tools because, okay, as shown in the slide, so even though you change the positions of N in one of these molecule, yeah, so you are getting the different chemical fingerprint. So actually NMR is very powerful, okay, for the structural isomers. So for the identification of structural isomer, yeah, so as you can see here, the fingerprints looks different, okay, yeah, even though the positions is slightly changed. Yeah, so this make NMR very powerful tools, okay, for the identification and for the characterizations. Okay, so then I will move on to the NMR spectral processing. Okay, yeah. So and I will start with the 1D processing. Yeah. So you can later when you get this slide, so you can click onto this page. Okay, so it will lead you to the Bruker website. Okay, because I put the active link. So after you have registered, okay, the registration is free. So after you register and then you log in, so you can get the TopSpin software, okay, from this link. Okay, so that's the software that we call the TopSpin, and this TopSpin software is a software that we use for the acquisition, we use for the processing, and we use for the basic analysis. Okay, yeah. So we have multiple software. So we have plenty of software that related to the NMR spectroscopy. So the TopSpin is our basic platform. Yeah. So you can get this TopSpin from the internet. Okay. So then from the link you can download our latest release in July. So this is the TopSpin 4.1.3. So you can download into your PC and then you can activate with the free license because you belong to the university. Okay, so if you belong to the university, you belong to the academia world, so you can get this top spin free license from this particular link. Okay, so if you are interested, please get the PDF and then the register and then try out this free software. Okay, yeah. So we also provide the step-by-step installations guide, okay, for you, okay, to help you, okay, in the process, installations and how to activate the license. Okay, so this link again is active. Okay, you can click onto it and then it will link you to the it will lead you to the respective website. Okay. So now for the processing, I will talk about the two important nuclei, as I already mentioned, the protons, okay, 1H, and the carbon-13 nuclei, okay. So I will start with the proton nuclei first, okay. So I will talk about the NMR processing, okay, or the spectral processing that is related to the proton NMR, okay, proton NMR. So we have some topics to cover under this 1D proton, okay, 1D proton. So first I will go through the processing and then I will show you the how to do the corrections, okay, yeah, or the baseline corrections. So if you get the NMR spectrum from the spectrometer, if the data is not fully processed, so you may get this type of result. So as you can see here, the peaks showing up and down. Okay, so this is the partially processed spectrum. Okay, partially processed spectrum. So usually you need to go through some a quick step. Okay, usually a quick step to get everything into the positive. So the point here, the proton NMR, okay, anti-proton NMR, the spectrums always showed up the positive peak, okay, positive peak, okay, or the positive signal. So if the spectrum or the result is not fully positive, okay, yeah, we have the up and down, okay, up and down. So that is not processed completely, okay. So you need to make sure that your proton, 1D proton, is positive, okay, yeah, it should show up positive, yeah. So here this is to show you, yeah, the top spin, yeah. So you can load the data into the window by drag and drop, okay, yeah. So when you drag from here and you drop here, then you will load the NMR data, okay. So you can click the process spectrum, okay, to get the spectrum done by this button. You hit this button, so you get this spectrum. So as you can see here, that this process spectrum is considered quite good, okay, but a little bit it's not very perfect, okay. Yeah, you have some kind of a peak which is moving at the negative side, so it means that you may need a little bit touch up, okay, yeah. So this is to show the second example, okay, when you drag and drop, okay, and you hit this process spectrum in the top spin. So in this case, the result is perfect, okay, yeah. So you get the good process spectrum where all the peaks looks they are positive. So means that not every time that you need a touch up, okay, yeah, depends, okay. So in this case, let's say if you need a touch up, okay, this is belongs to the phase. So I have the button which is the adjust phase button that you can further fine tune, okay. When you click this adjust phase, so you enter this module. So you see that you have this red line. So if this is not red line, then you can click on the 0 and then you activate it. So we will try to make sure that this peak is a little bit symmetry and then they are positive. Okay, so this is we call the 0 order phase. So this is the first order phase, that is we try to adjust the positions, okay, that is far from this red line. So this red line is a 0 order and the rest is the first order. So if you adjust a little bit and then you feel happy, then you can click the save button. So now the spectrum is good, okay, in terms of the phase. But when you can see that the positions, okay, this is higher than this is a little bit lower. So this is the baseline, okay. You can use the command apbk, okay, minus f, okay, to process your spectrum 1D proton, so that you see that whether you can get the improvement in terms of the phase. So this apbk minus f is the command that we introduced some years ago. So later on, I will show you the new command, okay, yeah, for the 1D proton on the baseline, okay. So where usually if you have this phase which is not perfect, okay, Yeah, so you can further adjust with the 0 order and first order. So after you adjust the baseline, okay, like for example, the APBK minus F, okay, and you feel that the baseline is still not okay, yeah, then you can use the command APBK minus F. Then after that, if you found that the phase is not correct again, or you need to fine tune the phase, then you can do the phase correction. So usually the baseline corrections, the baseline corrections and the phasing is go forward and backward. So until we get the perfect, or until you get the result, which is the you feel happy with your result. So it means that the baseline and the phase, okay, so sometimes you need to go back and forth, okay, so that you can get the final result, which is the looks good to you, okay, yeah. Okay. Okay, then I will move on. Yeah, so as I said, the APBK minus F, okay, yeah, is the command that we introduced some years ago. So for the top spin that you are able to process, okay, and the process, you can use this APBK, okay. So the APBK minus F is the command that some years ago, but this is a new command with the latest release top spin 4.1.3. So this APBK, okay, will give the same result, okay, compared to the APBK minus F, okay. Yeah, so you can just key in this APBK, okay, as a standard proton processing, okay. So this is a new command, okay. So if you are interested to learn more about this command, so you can log into our website, okay. Yeah, so this is ActiveLean. So there's a webinar that are related to this deep learning. We call the deep learning example, okay, or we call the baseline corrections of the 1D proton. Okay, so this is the quick one. Okay, yeah. So APBK. Okay, please try it. Okay, if you have this software 4.1.3. Okay, for the phasing. Okay, for the baseline and the phasing. Okay, so there's two components: baseline corrections and the phasing. So if the auto phasing is not perfect, then you can try the manual as I showed. Okay, 0 order and then check with the first order. Okay, 0 order and first order. So baseline is to make sure that everything, the level go to the 0. Okay. So then the next step for the proton NMR, after we do the simple processing and then the little bit check on the baseline and the phase, so we'll go to the calibration axis, okay? So which is we call the spectrum referencing. So means that in the spectrum referencing step, very common that we look for the signal that is we purposely add to the sample. So this signal is the signal that come from special chemicals, okay, that give the positions or the resonance at about 0 ppm. So we have many molecules that are able to produce this signal at the 0 ppm, okay. Yeah, many molecules, okay. So this step is after you have this sample, they're able to produce the signal at the close to 0 ppm. So we can take this signal and then we put this signal to 0. So this is we call the spectrum calibrations, or we call the calibration axis. So this is only possible if you already add certain amount, little amount of this reference. So we call this is the chemical referencing substances, okay? Chemical referencing substances. So there are many substances that you can consider, okay? So as long as there is the component that you purposely add in, okay, yeah. So usually this is we call the chemical referencing references, internal reference also can, yeah. So this amount usually is very, very small, okay. Usually we try to get the less than 1%, okay, sometimes 0.3%, 0.1%, okay, yeah. We just need a little bit, okay, to show up the signal at the position close to 0. So we can make the signal become 0 after we calibrate. So there are many substances that we can consider. So TMS is the famous and the favorite molecule for the organic, okay, organic reference, spectrum referencing. So for those samples that is not dissolved in organic, then the TSP or the DSS are the options, okay. So these are the molecules that only dissolve in the aqueous, okay. So for the aqueous sample, then you only can dissolve in the TSP or the DSS with your solvent and your sample. So organic, so you choose the TMS. So for the oil-Chris, you choose the TSP or DSS. So you just need a little bit, okay? Make sure that you add a little bit, not too much, okay? Not too much, less than 1%. So this is the recommended concentrations or the volume per volume. So the TMS or the some other TSP or the DSS, okay, yeah, they are different, but they will give the same, okay, outcome. Okay, means that you can use this zero signal, okay, calibrate the signal close to zero to become zero, so that you can have the good referencing. Okay, so this is we call the referencing. Okay, so this referencing is based on the chemicals that you added to your sample. So it means that in the NMR sample, you have your unknown that you want to analyze with NMR. So you dissolve your sample into the you dissolve your unknown into the solvent. Okay, but at the same time, you also can add a little bit internal standard, or we call the chemical shift reference standard, into the sample, or you can add into the solvent, NMR solvent. Okay, yeah. So then you have this signal in your sample tubes. Okay, yeah. So the calibration step is very straightforward. So if you have this molecule in, you just key in the command SREF. So this SREF will try to shift the signal that is close to zero to become zero. Okay. So this is an example to show that if you have the internal standard at signal close to zero, okay. So after the measurement, usually they are not exactly zero. Okay, they are close to zero, but they are not exactly zero. So for this sample that you already have the internal standard that you already added, SREF is a command, and then you bring the spectrum to the zero. Okay, so this will make these calibrations very handy. So you just need to key in this command to make sure that the spectrum is at zero. Okay, yeah. So usually when you measure, so the position at the 0 ppm is not perfect. Okay, so you just need another step. Okay, SREF to bring this signal to zero. Okay, yeah. So this is we call the spectrum referencing. So sometimes, okay, yeah, so this internal standard can evaporate over the times, okay? So the signal may be lower, okay? So if this signal is too low, okay, and the command SREF is not work, so what can you do? So if you know that this is sure that this is the internal standard, but just too low, okay, yeah, you can go to this calibration axis step, okay, and you put your mouse cursor at the center of the peak, and then you left click, and then you click OK. You set the 0.000, then you click OK. So this is somehow like the partial automatic. It's not the fully automatic, okay? But you can always click this calibrate axis, okay, and move to the cursor to the peak that is close to zero, okay, and then to see whether you can bring this spectrum to zero. So most of the time, okay, the SREF works, okay, yeah. So for those example that SREF is not working, so you can calibrate with the manual. So if let's say if you don't have the 0 ppm, if you don't have any internal standard, if you forget to add the internal standard, all these internal standard already evaporates, okay? Yeah, we know that they are very volatile, okay? The TMS is very volatile. So even though you purchase the neutrality solvent, this TMS may evaporate over the time. So then if you don't have the primary reference, so then you can base on the second option, which is a solvent. So you can check the sample, what solvent that the sample dissolved. Okay, so from this solvent, you can look for the Bruker almanac. So if you have the top spin, you can go to the manual. Okay, here the setting here, and you look for the Bruker manual almanac, and you look for the solvent. Okay, NMR solvent. So this NMR solvent will lead you to the page, okay, that we already collected some solvent. So this sample is dissolved in benzene. So the benzene have the chemical shift of 7.16. So this 7.16 is we call the residual solvent peak. So it means that we look for the peak that is close to 7.16, okay? Yeah. So these peaks are very clear in this case, okay? Yeah, we see that this peak can be the solvent because it's much taller than our analyte. So you go to the calibration axis, the same thing. So you go to the peak there, you left click, and then you click 7.16. Then you can calibrate based on the solvent. So again, this is the second option. Okay, first we always look for the zero. So if you're able to get the 0 ppm signal, then it's the best. Okay. If the happen that the solvent is not the TMS or the internal standard is not there, then we can calibrate based on the solvent. So if you want to calibrate based on the solvent, first you need to check what is the solvent and what is the signal that related to your solvent. So the setting here, the Bruker-Armanet is always a good options. Otherwise, you can check from your NMR textbook. So you look for the solvent and then you check the solvent that is related to your sample, and then look for the residual solvent. So this residual solvent will give you some kind of hint where is the signal. So just the first example is clear, it's easy to identify. Okay, we have the solvent signal, which is very special position that's not overlap with our sample. So in this case, this is also very clear. Okay, yeah, we have the solvent peak. Okay, that is related to this particular chloroform. Okay, so you can set this signal that is related to the solvent, that is the chloroform here. Yeah, so now the spectrum is calibrated according to the solvent. Okay, so this is a secondary option or the secondary calibrations. Yeah, so of course, so we will prefer the primary. Okay, if you don't have the primary, then you still can calibrate your spectrum based on, or reference your spectrum based on the solvent. Okay, solvent. So then I will move on to the next step, which is the peak. Okay, so this the peaks is the step to label the positions in the spectrum. Okay, so we know that we have a number of signal. We're not just getting one signal. So how to label the positions? Okay, so this is the process called the peak. Okay, the picking. Okay, yeah. So this is the example to show you. So after you calibrate, okay, after you have already calibrated your spectrum, okay, so now we move on to the next step. So the labeling the peaks, okay, can be executed very fast, PPS. So when you click the PPS, so you label the peak. So very easy, okay. So you just click the PPS, then all these will be labeled. So you'll see that this automatic labeling, okay, it will also detect. It will also detect the So I think the participant have accidentally turned on the video. So can you mute yourself? Can you mute yourself? Okay, thank you very much. Yeah. So this is the to adjust the threshold. Yeah. So you can adjust the threshold with this M. So you can move this box up. So yeah. So if the picking PPS is too sensitive, so you also pick the peak that is at the lower position. So you can shift this line up so that you only can you can label only the main peak. So you will not delete all the peak at the lower position. Okay. Yeah. So with this picking PPS, so it's quite easy to handle. Okay, so you just need to set the threshold. Okay, so if you found that this threshold is okay, then you can save and return. Okay, yeah. Of course, you can also delete those pick that is not necessary. So you can go to the picking modes. You click on it, and then you move to the point that you want to delete. So there's an option here: delete from the region that you define. So let's say this label that is not important, so you can drag with the mouse and then you delete with these regions. So this is again, depends on how complicated your spectrum. So if you want to fine tune this, then probably you take some time. Okay, let's say a few minutes. Okay, to clean up the label so that you only have the main peak that is only labeled. So just now we can set the threshold. Yeah. So sometimes this threshold is not perfect. So then you need to move on one by one, okay, manually to check, okay, whether which peak have to be label have to be removed, okay. Of course, you can remove, okay, with the region, define region. You can also add, okay, yeah. So you have the flexibility to add the label. You can have the flexibility to delete, okay, the region. Let's say, yeah, this is the important signal should be labeled. So you go to the pick module, and then you activate this button. Okay, this button, yeah. So then we can go to the point here, and then you left click, then you label. So this is the manually label the pick. Okay, so you have the PPS as the automatic pick label. Set the threshold is another one. You also can manually add the pick. Okay, with this picking module, and then you go to the pick, and then you left click, and then you will be labeled. So the software will show as a different color. Okay, one is in the red color, okay, which is the automatic pick labeling, and then the manual labeling will be shown in the green. Okay, yeah. So this is the picking module. Yeah. Then I will move on, yeah, to the integration. Okay, so the integration is the step that we try to calculate or determine the area under the curve. Okay, so this area under the curve, okay, can be integrated very easily. Okay, with some options. Okay, yeah. So these integrations, so for example, this is a 1D. Okay, so after that, after you calibrate everything, so you go to the integrate. So you can integrate, that is a top-down options that you can choose, okay, the arrow here, yeah. So these options, you can have the auto integrations, okay, yeah. So but you can click these auto integrations to see how's the outcome, yeah. So when you hit this arrow and then you hit the auto integrations, so it'll take you some time to complete the auto integration. So as you can see here, that these auto integrations will take the area, and then the software will determine it by itself, and then it will try to integrate. So usually these auto integrations is not perfect, especially when you have the close peak, okay, the overlapping peak. So you take everything in one, okay, yeah. So if this is the case, then you can try some other options. So there is the options that you can try, which is the APBK minus F. Of course, you can try with the APBK. So as I already mentioned, so this APBK minus F or the APBK, okay, in the newer versions, okay, we also perform the integrations, okay. So as you can see here, that these integrations, again, for the overlapping is still not very perfect, okay, yeah. So it means that for this automatic integration, sometimes it's quite challenging, yeah. So you may not get the very perfect result, okay, for the integral. So then we have another option, so called the SIG-RAG. So SIG-RAG is considered quite a new options, okay, that allow you to perform the integrations. So when you key the SIG-REG, okay, so then the software will try to perform the integrations, okay, yeah. So you have the SIG-RAG that able to this overlapping, okay, into the different integral. So actually the SIG-RAG is considered the much better options, okay, for the integrations, okay, yeah. So you have the, if you want to fine tune, then of course you can fine tune, okay, yeah. So this is the area on the every point, okay, yeah. So this is from the SIG-RAG, okay. So instead of it take everything and then it integrates, so the SIG-RAG can recognize some of the peak, and then can be they can integrate according to the main signal. So of course you can fine tune, as I said, yeah. So if you are not happy, yeah, you can fine tune. So you can check. So this integral you can calibrate as well, yeah. So you can calibrate this integral if, let's say, you know that this signal it belongs to 1 proton. So you can calibrate to this 1 proton from this integrate, and then go to the center here, right click, and then you calibrate. You select the integral and then you calibrate. So now this is become 1. So the rest will go according to this 1. Okay. Yeah, so it means that this is all value I will refer to this particular 1 reference point. So one of the SIG-RAG, the result showing here, yeah. So it's treat this as a 1 signal. If you want to make this separate, so you can cut, okay, you can from this integrate, you can activate this button, go to the center, and then you can do the left mouse click, okay. So this button will allow you to make the integral cut, okay. So if you feel that this integral is not related, so you can delete. So you go to the center here, you do the right click, and then you delete. So it means that you can do a lot of things with this the integral module, okay. If the SIG-RAG is not perfect, okay. So let's say, yeah, you see before that, okay, yeah, it should supposed to be only this big, but not this. So this one you can delete. So you can cut it and then you can delete the remaining. So this integral is the important tools and powerful tools, okay, to make the area under the curve calculations. However, if you have the overlapping, okay, if you have the overlapping, or you say the spectrum with not the very perfect resolutions, baseline resolutions, so you might have the error, okay, yeah. So the integrations module works best if you have the well-separated peak. Okay, if you have the well-separated peak, means that all the signal are well separated, while isolated, then you can get a very accurate value. Yeah. So of course you can activate these buttons, okay, to display the integral curve or to hide the integral curve. Okay. So this table integral tabs, okay, will lead you to the table, and you can copy this integral and then you can paste it to the Word or Excel. Yeah. So this is from the top spin module. Okay, you can click on the integral. So this button, you can activate the integral, whether you want to hide the integral curve or not. Okay, yeah, or you want to hide the integral label or not. So all these are related to the integrations. Okay, yeah. So hopefully this is clear to you. Yeah. So SIGREG, yeah, is the consider a relatively new command. Okay, and actually this is our first machine learning command. Okay, yeah. So if you are interested, of course, okay, we have the webinars. Okay, by our colleagues. Okay, yeah, you can join. This is on-demand versions, but the outcome is actually the SIGREG will give you the automatic integration much better than the classical algorithm. Okay, yeah. So we already found that this is considered quite a big improvement. Okay, in terms of the integration. Of course, if you have the overlapping signal, yeah, this SIGREG may not be perfect. Okay, so it still need your expertise, okay, to define the regions, okay, that is belongs to your sample. Yeah. So next, I will move on to the carbon nuclide. Okay, I will move on to the carbon nuclide. So the carbon nuclide, in terms of the processing, is very similar to the proton NMR. Okay, so because of the timing, so I will go through some important key step. Okay, in the processing. Yeah. So as you can click the process tab. Okay, to get the process spectrum. Okay. So when you compare the proton NMR and the carbon NMR, as I already mentioned, proton NMR is the most sensitive nuclide, okay, in the NMR spectroscopy of the natural abundance and because of the high magnetic ratio. So for the carbon NMR, yeah, so this carbon NMR usually give us the better signal resolution, okay. Yeah, this is the plus point, okay, yeah. So you get the better resolutions in the carbon, yeah. But however, yeah, as I said, yeah, the carbon NMR, because of the natural abundance of the carbon-13 nuclide is only 1.1%. So the sensitivity is not as great, okay. Yeah, but in terms of the application, so actually the carbon is very common, okay, because of the better resolutions, okay. Yeah, we do not see the much overlapping in the carbon unless you have the symmetry. And in the carbon experiment, yeah, so we have number of carbon experiment that is considered routine, yeah. So apart from the standard carbon-13 experiment, so the depth experiment is also quite useful. So we have the depth DEPT is the kind of or the group of NMR carbon experiment that allow us to detect, okay, the CH3, CH2, and CH in the different modes. So this is the variations of the carbon. So we know that the proton in the molecule, they are bonded. If they are bonded, so they can bonded to most of the times carbon isotopes. Of course, the proton can be bonded to oxygen. Yeah. So I think the participants forgot to unmute themselves. So please mute it. Okay. Yeah. Yeah. So for the carbon, for the proton, so I think the participants still forgot to mute. So please mute. So we are. Hello. Yeah. Please mute yourself first.
Hello.
Yeah.
Miss CL Chong, please mute your microphone, please.
Thank you. Yeah. So the carbon experiment, this is the options that you can consider. Yeah, so the 45, 90, and the 135. So as I said, the proton is the most of the time proton is attached to the carbon. Okay, of course the proton can be attached to the oxygen in the OH group, or the proton can be attached to the nitrogen. Okay, in the NH group. So if the proton attached to the carbon, so we have three different possibility. Okay, if the proton attached to the carbon, you have three different possibilities. So either CH3, CH2, or CH. So these are the different, we say different carbon multiplicity. Okay, different carbon multiplicity. So in the carbon experiment, for example, in the depths, so we have the options, okay, to show we have the option to show that the different group, okay, in the carbon. Okay, so in this case, I will show you, okay, one of the latest pulse or latest NMR experiment is called the depth Q. So this depth Q is the extension from the classical depth. So in the classical depth, I already mentioned that the depth 45, depth 90, depth 135. So this depth Q is the latest carbon experiment that able to give us the informations about the CH3 and CH from the CH2 and the quaternary. So as I already said, if the proton is attached to the carbon, so you have three options: CH3, CH2, CH. Okay, so this CH3, CH2, and CH from the carbon edited version. Okay, edited versions. So for example, in the depth, so we're able to tell, okay, even to differentiate the difference in terms of the grouping. So the depth Q is able to separate the CH3, CH from the CH2 and quaternary, which is showing in the negative phase. So the CH and the CH3 will be in the positive phase. So it means that the depth Q is very powerful. Okay. So for the processing, okay, let us go to the processing. Yeah. So for the carbon experiment, so when you drag in the carbon data, yeah, from the top spin. So if the spectrum is not processed, you hit the process spectrum. Okay. If you drag and then you see that the spectrum is processed, then it's fine. So if not, then you hit the process spectrum. Okay. If they are not displayed, then you need to hit the process spectrum. Okay. So this is always a quick step. Drag and then you hit the process spectrum. So as you can see here, that this is the one of the experiment called the J mode. J mode is APT. Okay, it's another versions of the carbon. Yeah, that is the more famous one. Okay, yeah. So in the depth, okay, let's say when you drag in and then you found that, okay, the peak is the positive, okay, and then if you have some kind of the phase distortions, then you may need some kind of phase manual phasing, okay, yeah, fine tune, yeah. So in general, yeah, so the process is quite straightforward. You drag and drop, and then you hit the process spectrum, then it's done. So if the spectrum is not perfect, in terms of the phasing, yeah, so this is perfect, yeah. All these signal from the carbon are positive, okay, yeah. So it depends, okay, yeah. So sometimes if you have some distortion in terms of the phasing, then you need the manual phasing, okay, yeah, to adjust a little bit. So this example is also quite straightforward, fine. So all the signals are positive. So we have one example that is not perfect, okay, yeah. So this is the perfect, okay, yeah. So we can open up, okay, we can overlay, okay, or you can multiple display from this from this button. So you can hit this button and then you can drag different traces, okay. So as you can see here that we have the standard carbon, which is showing at the blue trace, okay. So the rest are the different variations. So you can activate or you can increase the intensity, highlight by click on the box and then you scroll your mouse, okay. Yeah, scroll your mouse so you can increase the intensity individually. So when you compare, this is the regular carbon, this is a standard carbon, and the carbon signal that is missing in the depths, okay, the standard depth, these are the quaternary. So if you see the signal here but you don't see the signal from the depth, means that these are the quaternary. You only will see the quaternary in the depth, in the regular carbon or the APT or the depth Q. Yeah. So that is one. So the next thing is the CH2 will be always negative. Okay. Yeah. CH2 will be negative. So if you have the CH2, yeah, so for the 135, CH2 will be negative, yeah. So if you see that here, yeah, so in the APT will be also the negative, the red color will be the negative. So the 135, the CH2 will be negative, yeah. So, and the quaternary will not show in the top two here. The quaternary only will show in the red, which is the APT and the regular carbon. Okay, so this is an example to show that yeah. So if you need to do some fine tune, so as I said, yeah, this is a tiny touch up. Okay, yeah. So slight phase imperfection. So you go to the same as a proton, you go to the adjust phase, and then this will be the red color will be 0. So you go to the 0, and then you click left click, and then you adjust. So when you adjust, so the rest will be affected a little bit. So you can take a full view and then try to fix the positions of the overall, okay, and then after that you fix with the first order, so to get the perfect result, okay, or at least the recently good result, okay, for the rest of the spectrum. Okay, so this is the 0 order phase, okay, and the first order phase. So sometimes you may need to adjust the 0, 1, and again to get the better result. Okay, yeah, so this is still need a little bit minor adjustment. Yeah, so means that if you need adjustment, then you go to the adjust phase and then 0, then you adjust a little bit, and then you go to the overall. Okay, yeah. So if you feel that all the signals are either positive or negative, yeah. So this is a depth. So you can have the positive and the negative. So it have to be all positive, the positive side. Okay, yeah. You don't have the mixed mode, mixed phase, and then the negative side you don't have the mixed phase. So then will be the perfect. Okay. So this is the final outcome, okay? Final outcome for the processing, okay? For the carbon. So before I finish up with the 1D processing, so now I will introduce the term, the command called the APBK. So this APBK is also considered a new command, okay, for the top spin 4 onwards, okay? So you can see that this is the NMR, this is the carbon NMR now, okay? So if you have this the result in your spectrum, okay, yeah, if you get this type of a carbon result, so you can consider the command called the APBK, okay? So APBK, what happened is it will try to do the phase and the baseline together. So you get this, okay? Yeah, this is quite straightforward. Yeah, you just need to key in the command APBK, so you are able to get rid of this, we call the carbon baseline rolling. So this APBK is considered a good option, okay, for your standard carbon processing. When you key the APBK, hit, okay, then done, okay. So this is the result from the APBK. So I will recommend you try this APBK, okay, in your carbon processing, okay, yeah. So if you need the fine tune, okay, then you go to the adjust phase and then you do the 0 order and first order. Yeah. So before I end up the 1D, yeah, so if you go to our top spin, yeah, so after you install your top spin, if you are interested, so there's a top spin command. So under this folder, yeah, so you can search this folder after you install the top spin in your PC, okay? So there are several commands that is related to the 1D processing, okay? Yeah, of course, we don't have time to go through everything, yeah, but some important command already show to you, yeah. So these are the top spin 1D processing command. So I think with the little bit times left, okay, I will move on to the 2D processings, okay. So the 2D processing is slightly different from the 1D. So we have some example to show, yeah. So usually the 2D processing, we will run the 2D after we get the 1D process done, okay. So after we get the 1D process, for example, the 1D proton, 1D carbon, then we will consider the 2D. So this is the one of the 2D we can drag and drop, okay. And this is sometimes you get some kind of message showing QF, MC. So we can take a look, okay, on what are this message, okay. So this is this is a general plot, okay. You will see that in the 2D, very often that you have the display from the top, we call the projection, and at the right side or the left side. So on the top, these are the projection, okay. So usually we can have two options: internal projection or the external projection, okay. So this is you can introduce the internal projection or the external projection. So this external projection usually is better recommended, okay, because it's sharper, okay. So we will look for the external projection if possible, okay. So how can we load the external projection? So you need the 1D, okay. So let's say you know that where you store the 1D data, and then you go to the 1D data while you're opening the 2D, and then you right click, and then you can show the external projection. So it means that it will load this external project, the 1D into the external projection. So depends on your NMR data. Yeah, if this is the homonuclear 2D, as you can see here, the X and the Y, they are identical, homonuclear 2D, then the projections can be loaded as a F1 and F2, okay? Yeah, so this is a homonuclear, means that the X and the Y, they are identical, okay? So when you have these projections loaded, okay, yeah, so you can see that, okay, now the peak is a little bit off, okay, yeah, compared to the projection. So this little bit off in the display is because of the SR, which is the spectrum referencing. So I already showed that we can reference our spectrum with the 0 ppm or the so on. So this SR will be labeled into the 1D. So it means that in the 2D, okay, you need to check the 1D, the SR, and then you go to the 2D. Yeah, this is a 2D, and then you key in the SR, and then you fill in this value from the 1D. So this SR is the spectrum referencing. So depends, this is a homonuclear. So you have the X and the Y, F2, F1 have to be the same, okay? Because this is homonuclear. So when you fill in this number into the homonuclear 2D, then when you zoom in again, so now you'll see that now the peak will be aligned nicely under this line, okay? Yeah. So the positions of the peak will be now line up with your projection, which is the external projection. So when you load the external projections, very often that you need to have this SR from the 1D. So of course, we can take a look, okay? Yeah. So in this example here, this is a 2D that's showing some kind of the QF, okay? So this is the example called the cozy experiment, 2D cozy. So the analysis I will come in the second part, okay? So this QF means that this is the non-phase sensitive, okay? Non-phase sensitive. So the QF usually with the MC, okay? Yeah. So, and when you take a look at the cross peak, so these are the NMR signal, okay? So if you found that the signal are not very strong, okay, yeah, you want to make the signal sharper. So there's a command that you can consider, NLEV, and then you key in some number. So when you key in the NLEV, okay, so this is the default number from Bruker, 6, okay. You can increase to higher number, okay, and then you hit OK. Yeah, so this is the first command, NLEV, and then after that, you can use the second command, LEV, CALC, okay. When you hit enter in the command, you will make this cross peak sharper. So this is the important processing for all the 2D, okay, to make the intensity sharper. So now we move on, okay, to the 2D experiment. So this is another 2D experiment. So yeah, the square is always when you have the X and the Y, they are identical. So when you have the X and Y, they are different. So usually you turn off the square. So we'll turn off the square. So again, yeah. So in this two X and the Y, they are different. So we call the heteronuclear. So this dimension, yeah, this dimension is we call the F2 dimension. Usually is from the proton. The F1 dimension usually from the carbon. So if you want to load the external projection, similar to the previous example, you need to know where is the 1D, okay? So where is the corresponding 1D to this sample? So let's say this is the sample number 10, okay? This is 1D. Then for the carbon, yeah, this is the number 11. Then the same, yeah? So when you zoom in and if the peaks are not lined up, so this will be mainly due to the spectrum referencing. So you need to check the SR from the 1D, okay? You need to check the SR from the 1D. So you go to the 1D and then you go to the 1D and then you check the SR. So if you already get the SR, you can copy and paste, okay? So this proton is the F2, okay? F2, proton is the F2. So you just fill in this SR in the F2. Of course, if you already calibrate also the carbon, then you can go for the carbon SR to check the SR. Yeah. So if you already calibrate the 1D proton, 1D carbon, then you should check both, okay? Yeah, because you have two different SR in the 1D processing. So you just need to copy this SR and then go to the 2D again, drag and drop, and then you clean the SR, and then you place it at the appropriate positions. So you have two positions, F2, F1. So this F1 is for the carbon, F2 is for the proton. So now this spectrum is processed, okay? Yeah, and it calibrates, okay, according to the signal that is you already referenced, okay. So of course, similar to the previous example, yeah. So we can increase the contour level with the command NLEV, okay. Yeah, same as the homonuclear, yeah. So just this is the heteronuclear, okay. The X and the Y are different, so that's why you have the two different SR, okay. But the processing, the rest of the processing is the same. So after you key in the number, then you use the same command again, LEV CALC, to make this cross peak sharper, okay. Yeah. So this is the standard processing for all the 2D, okay. Yeah. So after if you're happy, okay, then you can save. So for the projection, just to take note, yeah, you need to know where is a 1D. So after you have the 1D, then you can introduce the external projection from this box or from this option, right click, okay. If you have the 1D, then you just right click. So this is another example of the 2D, yeah. You drag in, okay, yeah, you have the 2D, yeah. When you see the X and the Y, they are different. This is heteronuclear. So we'll turn off the square. So this is one of the example called the HMBC. So this is the third experiment, okay, HMBC. So in the HMBC, this is the proton. So you have the projections. Where is the proton? So this is a proton. So this is at the F2. You click F2, okay. And of course, you have the carbon projection. So this is the number 11. Go to there, right click, okay, display as 2D projection. And this is the F1, okay. So this is the F1. You hit F1. So now you take the external projections in, okay. And then we zoom in, okay. Yeah. So to see whether the cross peak, is it line up, okay. Yeah. No, not really, okay. Yeah. The cross peak is not really line up. So you means that again, you need the SR for this HMBC. So you need the SR from the proton, SR from the carbon, okay. Yeah, you need to copy the SR from the proton, and then you copy, and then you click OK, and then you go to the 2D HMBC, and then you paste at the F2, okay. So the F2, yeah, here, which is here, yeah, F2 is here, yeah, you just paste here, and then you need another F1, okay. So you need the 1D carbon, drag in 1D carbon, and then you hit SR, okay, and then you place this SR at the carbon, which you copy here, and then you paste into the 2D HMBC. So now the 2D HMBC, you drag in again, and then you click the SR, and then you place at the F1, okay. Yeah, so this is the same, okay. Yeah, so when you do the homonuclear, you only do it once, okay. But for the heteronuclear, you need to repeat the X and the Y, okay. And in the HMBC, yeah, so we have a very special pulse processing, okay. So as you can see here, that it asks you to do the XFB and the XF2M, okay. So what happened is in the spectrum, yeah, when you zoom in and when you take a look, okay, yeah, when you take a look, okay, yeah, so the result, okay, yeah, if you do the XF2M, yeah, okay, yeah, this XF2M is the command that you need to key in. So as you can see here, that it shows you the two different contour color. But when you key in the XF2M, it will convert to the single color. So this is the additional step for the HMBC. The HMBC, you need the XF2M to convert this to the magnitude mode. Okay, this is the magnitude mode. So the rest is the same. If you want to increase the contour level, then you click the NLEV, and then you just put in your magic number, and then followed by this LEV CALC. But just now, the XF2M is important in the HMBC processing. So you need to key in the XF2M for the HMBC. Yeah, that is the big difference compared to the HSQC. Okay, or compared to other 2D. Yeah, so this XF2M is important. So this example is to show the N15. So I think with the time, so I will skip this. Okay, yeah. So there are several 2D processings, okay, that the command. So I already show you some of the command that related to the 2D processing. So this 2D processing, this table can be accessed after you install the top spin. Yeah. So you can have this table with you. Yeah. Or the list with you. Yeah. So you can try out this 2D processing by yourself. Okay, with your PC. Yeah. So I think with the time, okay, I will finish up the first sessions for today's. Okay. So we have the break, but before we go to the break, so I will try to answer the questions from the participant. So yeah.
Thank you very much, Dr. for your, the session on, I think, on the NMR processing and also sample preparation. The first session was more on how to prepare the samples, and the second one is on how to process the sample. So, Dr. before I think the participant type in the questions.
Yeah.
I have question for you.
Okay.
All right. So it's just I think it's just quite a basic question, because you mentioned about using the deuterated NMR solvent. May I know what are the reason we need to use deuterated solvent rather than use the normal solvent?
Okay. Yeah. So actually, this is the good. Yeah. So in the classical applications of the NMR, so the deuterated solvent was introduced because this deuterated signal in the deuterated solvent will give the spectrometer reference signal. So this reference signal is checked at the spectrometer background. Okay, so if you use the deuterated solvent, so the NMR machine will check this deuterated signal at the background, and it will always calibrate this signal to the point that we already set. So what happened is, if you measure the NMR experiment at a longer period of time, let's say 1 hour or 1 day or 2 day or 3 day. So what happened is the magnet, okay, the magnet, which is a superconducting magnet, the field, okay, the magnetic field is not constant, okay. The nature of the superconducting magnet tend to drift, okay, means that the field will drift from time to time. So it depends on the design of the magnet, and it also depends on the whether it's the fresh magnet or the some years magnet, if we call the adult magnet. So for the fresh magnet, the drift is faster. So this drift can be can be detected by this the monitoring of this deuterium. Okay, so if you have this deuterium, so the machine at the background, they will know, okay, now the point is already drifted. So the machine will try to bring back, okay, the preset point. So without this deuterated solvent, so you cannot bring back this preset point. Okay, yeah. So that is one reason we use the deuterated solvent. So in the professional terms, so we call it the deuterium lock. Okay, you use the deuterium signal to lock the magnetic field. Okay, this is point number one, why you need the deuterium solvent in the classical NMR experiment. The second point is if you are using the deuterated solvent, so in the deuterated solvent, most of the atoms have been substituted with the deuterium. So we do not have the H, okay, that present in the solvent most of the time. Okay, of course, this will depend on the how high the deuterations. Okay, so if you purchase the deuterated solvent with the 99.9% or 95%, you will see the different level of the deuteration. So these deuterations will be observed in your NMR, especially in your proton NMR. if you buy the cheap grade deuterated solvent, so let's say, for example, the 95% deuterated atom, so you will see the bigger peak, okay, for your solvent. So this bigger peak, we call it residual solvent. Residual solvent means that the 5% is not the completely changed to deuterium. So you still have this residual solvent present in your deuterated solvent. Of course, if you purchase 99.8%, so this deuteration is high, so you have the smaller residual peak. So now we come back to the, if you try to consider this deuterations, the residual peak in the deuterated solvent. So usually these residual peak are small. So our interest is to analyze the sample. The sample contain many signal. So we will try to avoid, okay, the solvent signal that overlap with our sample. If you are using the deuterated solvent, so the tendency for the solvent to overlap with your sample is lower because the peak from the solvent is smaller. So your sample, even though there's a many signal, but the tendency to overlap with this deuterated solvent is less. So it means that if you try to measure, okay, if you try to measure your sample in the regular solvent or the routine solvent, so then you expect that is possible. Of course, you can measure your sample in the laboratory solvent. That is possible, but you will expect this solvent signal from the laboratory solvent is huge. So there's a high tendency that this huge tall signal overlap with your sample, and very often it can cover or it can mask your solvent signal. So in this particular case, you will need another step to reduce this laboratory solvent. So we call the solvent suppression. So it's not the consider so-called routine anymore. So that is possible. So if you measure your sample in the laboratory solvent, so you need to reduce the solvent peak by apply appropriate solvent suppression scheme, so that this signal from the solvent is reduced, so that you can observe your signal of your analytes clearly. And while we are reducing this laboratory solvent signal from the solvent suppression scheme, so we also gain the receiver for your analyte. So if imagine that if you have one sample that huge solvent, let's say 10,000 times higher than your analyte. So this analyte because it's 2 liter, okay, in the sample tubes. So the sensitivity is not that great. So you have the 10,000 times huge solvent, which is not our target, not our interest, but the NMR machine will thought that this is from the sample. So the receiver gain may not be optimal. So by kick away or by reducing this solvent signal with the solvent suppression scheme, we're able to gain the sensitivity of this analyte. So this non-deuterated solvent example application actually is very common in the synthesis lab. So we know that in the synthesis, the organic chemists or the synthetic chemists, they perform the chemical reactions in the non-deuterated solvent conditions. So usually they will tend to bring their sample from the reactions medium and then straight away measure with the NMR. So that is common, okay? Yeah. So but they need to apply a special technique to remove the solvents, okay? So that the signal from the solvent is not overlapped with the analyte. And usually the measurement is quite fast, so they do not need the lock, okay? Yeah, as long as the magnetic field is the concern, so at the experiment time is short, usually less than an hour, so they do not need a field lock, okay? Yeah, so that's why there's also in the group of application that related to the non-D NMR, okay, which is the NMR sample measurement in the non-deuterated conditions. Now, I hope that this is clear.
Thank you very much, Dr. T, for very, detailed explanation why it's important, especially any researcher that doing natural product research using deuterated solvent rather than using the normal solvent, except for the organic chemists that always use run the sample by real time, right?
Yeah, correct.
We have question here asking because you mentioned on the integration on the carbon uh, uh, several features that we can use, for example, that 45, that 90, and so on and so forth. So what's the difference between that 135 and J mode APT?
Okay, yeah. So this is also a very interesting question. So the J mode, yeah, the J mode, or we call the APT, they are the same. Yeah. So we the attached proton test. Okay. So the informations that give by this J mode APT and the depth Q. Okay. Yeah. More precisely, it's a depth Q. Yeah. Depth 135 is not the newer version, but the depth Q is a version new. So these two experiments, they are identical, okay, in terms of the information.
Okay.
Yeah. So but the depth experiment is more sensitive. Yeah, much more sensitive compared to the APT. Yeah. So people will tend to know the APT because the APT in the classical way, they can deliver informations of CH3, CH2, CH, and CQ. APT is very famous in the CQ, quaternary carbon, but the depth is not famous in the quaternary. Okay, until we introduce the depth Q experiment that also detect the quaternary. But now, when you compare the informations between the APT and the depth Q, so they are the same, but just the depth Q, the depth is more sensitive, much more sensitive, about 4 times more sensitive. Yeah.
All right. Can try use it the depth Q after this.
Yes.
All
Yeah.
right. Thank you, Dr. G. I think Dr. Tay, because we are running out of time, and now is time's break before the next session. So again, thank you very much, Dr. Tay. We for all participants, we will have 10 minutes break, and then we will come back later for the second session with Dr. Tay.
Yeah. Thank you very much. So see you later.
See you later.
i-CRIM Centralised Laboratory was officially founded in 2007. i-CRIM Centralised Laboratory provides technical and consultation services to scientific communities. In i-CRIM Centralised Laboratory, we have 3 main labs: Molecular Structure Characterization Lab, Physical Characterization Lab, Morphology Lab. Each lab is equipped with high-end instruments and run by well-trained personnel. i-CRIM Centralised Laboratory offers a wide range of technical analysis, especially in material sciences, mineral studies and elemental analysis, surface analysis, caffeine analysis. Molecular Structure Characterization Lab is equipped with liquid chromatography mass spectrometer, TOF, nuclear magnetic resonance, NMR, gas chromatography mass spectrometer, automatic polarimeter, FTIR, HPLC. Physical Characterization Lab is equipped with Auger electron spectroscopy with XPS, single crystal XRD, X-ray fluorescence, X-ray diffractometer, photoluminescence, surface profiler, ultraviolet PIS. Morphology Lab is equipped with field emission scanning electron microscope, FESEM, particle size analyzer, scanning probe microscope, atomic force microscope. i-CRIM strives to provide our clients with quality scientific and technical services, capacity building, competitive rates. For more information, please visit our website at www.ukm.my/i-CRIM. Welcome to i-CRIM Centralised Laboratory, University Kebangsaan Malaysia. i-CRIM Centralised Laboratory was officially founded in 2007. i-CRIM Centralised Laboratory provides technical and consultation services to scientific communities. In i-CRIM Centralised Laboratory, we have three main labs: Molecular Structure Characterization Lab, Physical Characterization Lab, Morphology Lab. Each lab is equipped with high-end instruments and run by well-trained personnel. i-CRIM Centralised Laboratory offers a wide range of technical analysis, especially in material sciences, mineral studies and elemental analysis, surface analysis, caffeine analysis. Molecular Structure Characterization Lab is equipped with liquid chromatography mass spectrometer, TOF, nuclear magnetic resonance, NMR, gas chromatography mass spectrometer, automatic polarimeter, FTIR, HPLC. Physical Characterization Lab is equipped with Auger electron spectroscopy with XPS, single crystal XRD, X-ray fluorescence, X-ray diffractometer, photoluminescence, surface profiler, ultraviolet VIS. Morphology Lab is equipped with Field Emission Scanning Electron Microscope, FESEM, Particle Size Analyzer, Scanning Probe Microscope, Atomic Force Microscope. i-CRIM strives to provide our clients with quality scientific and technical services, capacity building, competitive rates. For more information, please visit our website at www.ukm.my/i-CRIM. Welcome to i-CRIM Centralised Laboratory, University Kebangsaan Malaysia. i-CRIM Centralised Laboratory was officially founded in 2007. i-CRIM Centralised Laboratory provides technical and consultation services to scientific communities. In i-CRIM Centralised Laboratory, we have three main labs: Molecular Structure Characterization Lab, Physical Characterization Lab, Morphology Lab. Each lab is equipped with high-end instruments and run by well-trained personnel. i-CRIM Centralized Laboratory offers a wide range of technical analysis, especially in material sciences, mineral studies and elemental analysis, surface analysis, caffeine analysis. Molecular Structure Characterization Lab is equipped with liquid chromatography mass spectrometer, TOF, nuclear magnetic resonance, NMR, gas chromatography mass spectrometer, automatic polarimeter, FTIR, HPLC. Physical Characterization Lab is equipped with Auger electron spectroscopy with XPS, single crystal XRD, X-ray fluorescence, X-ray diffractometer, photoluminescence, surface profiler, ultraviolet BIS. Morphology Lab is equipped with Field Emission Scanning Electron Microscope, FESEM, Particle Size Analyzer, Scanning Probe Microscope, Atomic Force Microscope. i-CRIM strives to provide our clients with quality scientific and technical services, capacity building, competitive rates. For more information, please visit our website at www.ukm.my/i-CRIM.
All right, I think it's already 10 minutes. Break session has already passed. So now we can move on to the next session with Dr. Tay. Dr. Tay, please.
Okay, thank you. I will share the screen again. Okay, so can you see the screen, right?
Yes.
Okay, thank you. Yeah.
Thank you, sir.
Yeah. So we'll move on to the second parts. Yeah. So according to our schedule, so I will in this sessions I will talk about the NMR spectral analysis using the 1D and the 2D. So if you have the NMR result from the NMR spectrometers, so these are the 1D and the 2D spectrum. So you already went through the very basic processing for the 1D and the processing for the 2D. So next we're going to work on this NMR data, which is NMR spectra. So as we know that the NMR result, okay, yeah, from the 1D and the 2D, yeah, so all these NMR spectra from 1D and the 2D, they give us the very useful informations for the structural identifications and structural characterizations. So all these informations can be briefly grouped into three, okay? First, chemical shift. Second, coupling. The third, intensity. So this information actually you also can call it as a general, the terms for the general of information is NMR primary observables, okay, or the NMR parameters, okay, primary parameters. So these informations can be collected in the different form, different way. So this how to put this into different form or different way. So we call it different NMR experiment. So the different NMR experiment will give you the different way of to present these basic informations, okay, which is the coupling, chemical shift, and intensity. So all these are the different experiments, okay, yeah, they're already shown, yeah. So these 1D proton, 1D carbons, and then these are the homonuclear experiment, heteronuclear experiment. So usually the homonuclear experiment, we will display in the square form, square, and then the rest will be the rectangle. Okay, so where you have the X and the Y is the same, it's a homonuclear. X and the Y they are the different, so they are heteronuclear. So just take a look, okay, for the quick one. So if you look at the NMR spectrum, so we know that this is come from the sample, and the sample give this signal is because they contains the active nuclide. So this active nuclide, they possess the magnetic moment. So you can say that they have this gyromagnetic ratio in their nucleus. So when you look into the NMR spectrums, so this is the typical 1D experiment, 1D proton. So you'll see a number of peaks, a number of signal, or sometimes we call it, there are different types of the resonant frequencies, okay, that are spread along the x-axis, okay. So this chemical axis, okay, this axis, so it's a range from the small value is on the right, and then the larger value is on the left. So this axis is the axis that we call the chemical shift, okay? This axis is called the chemical shift. So the signal will spread along this chemical shift axis. And you can have the unit of, we call the label called ppm. So this label ppm already shown in the processing. You can use the pps, okay, to label the peak, okay? So for example, here you have the signal here, that you can say that this signal is resonate or appear at the 12.22 ppm. So we have another signal appear at the 7.21 ppm. So all these are the locations, okay, to label where is the positions of the signal. And the 1D informations tell us about the chemical shift, and this chemical shift can be related to the functional group. So different functional group will have the special regions, okay, for the signal to be appear, okay, yeah. So so this, if you have a CH3, yeah, all these CH3 will give you the same signal positions, okay, yeah, same signal positions. But we know that we don't have only this methyl group, but we have the methyl group that attach to the different chemical environment. So this chemical environment, or you can say different functional group. So this different functional group will give, okay, the signal varied from one to another. So instead of we are getting the same chemical shift, okay, because of the different chemical environments, okay, then this signal will resonate at different position. So this will be the first observations that you can obtain, okay, from whether it's a 1D or the 2D. So we are getting the many signal, okay, multiple signal, even though we are saying we are detecting the 1H proton, but because this 1H proton is attached to different group, chemical group, okay, or the different functional group, so they will appear at the different positions. So we take a look at this example again, quite simple, straightforward. So we have the chain here, we have the H here attached. So we are detecting the proton, okay, yeah, proton NMR. So we will have this, for example, the chemical shift dispersions, okay, and then we have all these chemical shift signal. So these are the resonant frequency. So in the NMR spectrums, okay, the signal positions that you observe here actually is not related to the molecule that you draw. It's not related to the structure that you draw here, but it's more related to the chemical environment where the atoms are situated. I hope that this is clear to you. So when you draw the molecule like that, on the left, you have the orange, blue, purple, red, pink, green. So not necessary that when you have this, when you translate this molecule way that you draw into the chemical shift, so you will go like the orange, blue, no, okay? It depends, okay? Yeah. So these positions in the chemical shift in the NMR plot will depend on the molecular environment, okay? It is the molecular environment that determines where the signal can be appeared, okay? So in this case, so the H, okay, the orange and the blue, okay, yeah. So in this case, the blue here is at the first position instead of the orange. So the second one signal is the orange. So it depends on the chemical environment. So for example, you have the signal from this CH2 and the signal from this CH2. So if you have the CH2, which is we call the methylenes, okay, in this case, these methylenes, this group of methylene will give you the chemical shift at 2 different chemical shift. Means that the proton NMR will be different in this CH2. Whereas in this CH2, they will give you the single chemical shift for the proton. So this is also very common, okay, very common in the NMR as NMR analysis. So you may have the CH2 that give the two different signal, okay, for each protons, and you may have the NMR result that give the single chemical shift for the CH2 proton, okay. Yeah. And then the last one is the CH3, okay. Yeah, you will have the signal that belongs to the CH3, okay. So in this case, this is a green color. So this is the first chemical shift, okay, yeah, that you observed. Yeah, this is related to the molecular information, which is the functional group, okay, functional group. So the second observation that you also can see from here is the area, okay. You have the smaller area here, we have the bigger area here. So if you observe carefully, this area belongs or is contributed by the proton, one H. So if you have 3 protons, okay, that give rise to the NMR signal, so the area is triple. So the area, or we call the integral, is another important NMR parameter that we're going to discuss later. Okay, yeah. So this is another observations. So let's take a look, okay, again. Yeah. So the signal, where the signal appear is related to the chemical shift, okay, and it can be traced to the functional group. So different functional group will give you the different chemical shift. Okay. So the next observations that we can see from the NMR result is we are always not get a single peak per frequency. Very often, okay, we are getting multiple peaks, okay, per locations. So instead of we are getting single peak, very often, most of the time, we are getting multiple peak. So we call the multiplets, okay. We will get the multiplets, especially in the proton NMR. So we are looking at the proton NMR. This is a proton NMR. So we can tell this is a proton NMR easily from the scale. So as you can see here, this scale is less than 100. So less than 100, the common nuclei is a proton. Okay, so this is a proton NMR, and we are not getting a single peak for the signal every time, but we are getting multiple peak. So the question now is why you getting the multiple peak? Okay, instead of getting the single peak, why you are getting the multiple peaks? Okay, which is the multiplets. Okay, multiplets. So we call it, these are the coupling. These are the result from the coupling. So instead of getting single peak, because of the coupling, so we are getting multiple peak. Okay, because of the coupling, we are getting multiple peak. Of course, we can calculate with the equations, okay, but we are not going to the detail. So this coupling, okay, yeah, to make it easier to understand, okay, the coupling is because when you measure a sample, okay, we are not just measure an atom, we have millions of atoms. So I already shown, okay, as already mentioned, we have millions of atoms, and all these atoms, they are magnetically active, okay, so that the NMR can be detected. So they have the gyro-magnetic ratio, so they have magnetic moment. So when they have this magnetic behavior, so we expect that they're able to interact, okay. Either they can attract or repel. So when they interact, repel or attract, so we say they couple, okay. So that's why you have the coupling. So this coupling can involve the same types, so homonuclear coupling. So when you have the interactions between the same types of nucleus, so it will give the signal split, okay. So instead of you getting single peak, you are getting multiple peak, you are getting multiplet. So this multiplets is the effect from the coupling, okay. So when you couple, when the nuclide couple to each other, then the signal will be splitted, okay. So this splitting from the similar nuclide homonuclear. So of course, in the molecule, you also have these carbon-carbon atoms, okay. So this gray color indicates that these are the carbon atoms. We are not just having one atom in the molecule, but we have many carbon atoms that join through covalent bond. So we will expect the carbon-carbon nuclei, and we have the carbon-carbon-13 nuclei. Then we expect the carbon-carbon-13 nuclei interaction, which is also the homonuclear coupling. So when they couple, the signal will split. So you have the splitting from the homonuclear carbon, okay. And of course, in the molecule, because we are joining through covalent bond, so we also observe this heteronuclear proton-carbon interactions, magnetic moment, okay, through magnetic moment, magnetic interactions. So when they interact, they will couple. When they couple, then the signal will be splitted. Okay, yeah. So this coupling, okay, the interactions between the similar types of nuclei or the different types of nuclei, it can be operated through two options, okay, through covalent bond, through covalent bond. So we call the scalar coupling. So it means that you need the covalent bond to join this magnetically active nuclide together. Okay, this is very common in the molecule. Okay, or this magnetic moment, the magnetic interactions, for example, the proton-proton interaction can be also operate through space. Okay, so we have two options: through covalent bond or through space. So through space means that they do not need to be close through covalent bond. They can be close through space. So these through space interactions we call the dipolar coupling. Okay, through space is we call the dipolar coupling. So through bonds interaction is called the J coupling or the scalar coupling. So we have two important coupling between the magnetic active nuclide. Okay, between the magnetic active nuclide. So we can either scalar coupling or the dipolar coupling. So in this webinar, okay, so I will focus mainly on the scalar coupling, okay, through bonds. Okay, yeah. So as we know that the atoms are not free moving, okay, so the atoms have to be bonded. So if you have the proton that is bonded to the carbon, for example, in the methyl group or the methylene group or the methyne group, so we'll expect that these are the magnets, okay, tiny magnet. So this tiny magnet, they're able to interact because of this covalent bond are very short, okay, very short. So this will bring this magnet very close through bonds. So when they are very close, they are near, they're able to interact. When they interact, they couple. When they couple, the signal will be splitted. So we will see this coupling, the one bond coupling, J1, okay? One bond coupling, J1, heteronuclear between proton carbon in the methyl group, in the methylene group, CH bond, J1, and this is a CH2 bond, methylene, and the methyne group, CH bond, in the in this example, for example, different configurations. So all these are the interactions between the one bond, proton, carbon 13. Okay, one bond, proton, carbon 13 interaction. This is very common in the molecule. Okay, because we know that the proton usually are attached to the carbon most of the time. Okay, most of the time. So this is a J1 coupling, heteronuclear scalar coupling. Heteronuclear scalar coupling. So can we see this in the most sensitive proton NMR? So we know that the proton NMR is the most sensitive experiment. So we will see that in the proton NMR, we are not getting single peak, as I already said. Because of the coupling, we tend to get multiple peak, okay? So on the left, you're getting the multiple peak for the proton NMR, multiple peak for the proton NMR. But we are looking at now the J1, means that the proton-carbon covalent bond. Can we see this proton-carbon covalent bond in the proton NMR? The answer is yes. So where is it? It's here, okay? So we see that we have the very big peak, okay? And beside that, if you go to the bottom of the proton NMR, you will see the very tiny peak. This tiny peak, very, very small, is usually less than 1%, okay? 0.5%, 0.5%, which is very, very low, okay? At this, the bottom, okay? At the bottom, we call the carbon satellite. So these are the signal that confirm or tell us where the proton is covalently bonded to carbon 13. So we call it carbon satellites in the proton NMR. So in the proton NMR, we can see the satellite signal. So this satellite signal is a proof of the proton that is directly bonded or single covalent bonded to the carbon 13. So let us go to the more detailed example. So let us take the chloroform. So this is a very simple molecule, the H, and then we have the trichlorine that is attached to the carbon. So if you look into the covalent bond, okay, the proton can be bonded to the carbon-12. So we know that the carbon-12 is the major isotopes of carbon element. So it's about 99%. And we have also the possibility that the proton is bonded to carbon-13. So as you can see, that this carbon-12 is not active, okay? It's not detectable, okay? This carbon-12 is not detectable by NMR. So NMR have no information about the carbon-12, but the NMR have the information about the carbon-13. So this carbon-13 is only 1% at the natural abundance. So what happened, okay? If you have this carbon-12 that is bonded to the proton, which is 99%, and this is non-active, so you see that the coupling. So the coupling you need the magnet, okay? If they are magnet, they will couple. If they are not magnet, they will not couple. So in this case, the proton and the carbon-12, this carbon-12 is not the magnet. So you will not see them couple. So what happens is when they are not coupled, the signal will not split. The signal will remain. So this 99%, the signal will remain as what it is, based on the chemical shift. But this 1% make the difference because of this 1% bonded to the proton, okay? And this is active. So when you have two magnetically active nuclei that is bond through covalent bond, they're able to interact within each other. So when they interact, so there are two magnets, when they interact, the signal will split, okay? So this splitting is based on the 2Ni plus 1 rules, okay? You can calculate how many signal, okay, that you observed, okay, for that particular frequency, okay? And you can also predict the intensity, okay? Whether you have the 1-to-1 ratio, 1-to-2-to-1 ratio through this Pascal triangle, okay? So we have two the analysis step, okay? So let us take a look, okay? So we know that this is the 99% which is attached to the carbon-12. So when you apply this 2Ni plus 1, this I will be 0 because this is non-active, okay? The carbon I is 0, okay? So it means that you will get the formula is giving you 1. Means that you don't have any split, okay? So this is the main signal from what you observe in the proton NMR for the chloroform, okay? For the chloroform. So when you measure the chloroform, you see the very tall peak, okay? So this tall peak is contribute to 99% of the total spectrum. But we know that there's 1% that is the proton attached to the carbon-13, and we expect the split, okay? Because they couple. When they couple, they split. So when you based on the same equations, okay, same equations, 2Ni plus 1, okay? So when you try to determine how many signal, so this 2, okay, is the formula, and is we have one neighbor, and then this one neighbor spin quantum number is spin half. So when you have this 2Ni plus 1, you get 2. It means that when they couple, they split. So in this 1% signal is splitted into 2, okay? Yeah, and the ratio is 1-to-1. So this 1-to-1 is through Pascal triangle. So we have the 1-to-1, 1-to-2-to-1, okay, 1-3-3-1. So all these are from the Pascal triangle for the first order interactions, okay? So you expect that this signal very, very small, okay, less than 1%, okay? This is the evidence because when the proton is bonded to carbon-13, okay? But in the proton NMR, you have this signal which is non-splitted. It's because you do not have the active nuclei in the sample, in this case, CHCl3, okay? And you can measure the distance from this signal to this signal. This will give you the coupling constant, J1, okay, CH. So when you look at the NMR, proton NMR again, okay, the signal for the carbon-13 is very, very small, but it is important, okay? So this is we call the satellite. This is contribute to about 1%. But the main signal, okay, this main signal come from the 99%, okay? In this case, they are non-single peak. In the chloroform, they are single peak because You don't have any other neighbor, okay? But in the molecule here, you may have some other neighbor. Their chloroform is very simple, only CHCl3, okay? But in the molecule, you may have some other neighbor. So this neighbor will contribute to 99%. And what are the neighbors that give you this 99% informations? So these neighbors are proton neighbor, okay? So we see that in the satellite signal, which is the carbon neighbor, okay? The main splitting or the main coupling in the proton NMR is not due to the carbon, but it's due to the proton neighborhood. Because we are looking at the molecule and the protons, they are covalently bonded. They will interact with each other because they are magnet. They are tiny magnet and they are able to interact through the covalent bond. If they are separate through three covalent bond, 1 bond, 2 bond, 3 bond. So these two nuclide proton, they will interact. So when they interact, so we call it they will undergo the spin-spin coupling. So this spin-spin coupling will give the signal split. Okay, when they couple, the signal will split. Okay, so as you can see here, that they will split in the same way. So it means that you will see me, I will see you. So they have the same coupling constant. Okay, same coupling constant. So in this coupling mode, okay, so we also will detect the proton that is attached to the same carbon. So this is, we call in chemistry, we call the germinal proton. So this is, we call the vicinal proton. Vicinal proton means that the proton and the adjacent carbon, and then this is adjacent proton. This is a vicinal proton. This is a germinal proton. So in the splitting, the spin-spin splitting, we will also observe the splitting from the germinal proton if they are different chemical shift. So it means that the purple and the red, hydrogens, the proton, they will split each other, okay, equally, okay. So when the blue, the red and the purple, they have the same coupling constant, okay. And for the CH2, okay, and if they are able to undergo free rotation and they only give you the chemical shift, so they will not split each other. But in this range, you will rather see the splitting or the coupling from the adjacent proton, which is a vicinal coupling. So the pink and the green, when they split each other, they couple each other. So they will give rise to the splitting pattern that correspond to the 2Ni plus 1 formula. Okay, yeah. So when they split, then you may have the overlapping. Okay, yeah. This is a common phenomenon. Okay, especially in the proton NMR, you will get the very congested and highly overlapping result if you have the close resonance. Okay, if you have the close resonance. So just take a look again. Yeah. The CH3 and the CH, so ideally they should have the two different chemical shift because they have belongs to different chemical environment. So this position depends on the chemical environment or the functional group. And because when they are joined, okay, they are close through bonds. So this proton able to interact. So when they interact, for example, the blue interact with the red. So this blue will cause the red to split. Okay, yeah, the signal will be splitted. So the similar thing, the red will also cause the blue to split. So the splitting is because of the proton-proton neighbor interactions. Okay, and you need the covalent bond for this, and this involves the homonuclear coupling. Okay, and when you observe this splitting pattern, you will know, if you're able to analyze, you will know the neighbor. Okay, yeah, if they are isolated, if they are well separated, you can get this pattern, and then you can trace where is the neighborhood. Yeah, of course. Okay, when you have the more complicated molecule, yeah, so for example, it continue further, so you have another group that is vicinal to this red. So any vicinal protons will cause the signal to be splitted further. Okay, so this will be the outcome from the total neighborhood. Okay, yeah. So this is the theoretical model that I want to show. But when you analyze your NMR result, the result that you have is the collections of the total environment that you observe the splitting as a total. Okay, it will not show you one by one. Okay, you will get the final one. So this is a total of the blue and the green environment that cause the signal to be splitting because they are magnets. So similar, yeah. So you need the covalent bond, okay, yeah. Without the covalent bond, you are not able to get this spin-spin coupling, okay, or the scalar coupling. So this number of the line can be summarized with this formula 2ni plus 1 rules, okay. And yeah, let's say if you have this side chain that is attached, so is it possible for this rate also to detect a signal from the proton neighborhood from here? So if you count the bond, 1 bond, 2 bond, 3 bond, 4 bonds, 5 bonds, okay. So for the proton-proton spin-spin coupling, proton-proton is not exceed more than 4, okay. More than 4 is not detectable. So this is more than 4. So this group will not interact. The magnet is too far, okay. It cannot interact with this red one. So you don't see the signal split from this group to the red. No, okay. So in the proton NMR, so you will see the J3, which is 3 bonds away. 1, 2, 3, 1, 2, 3. This is confirmed. Okay, this is confirmed. Vicinal coupling is a standard. Okay, germinal coupling is also a standard. Okay, J2 HH is a standard. J3 HH is a standard. But J4 will depends on the structure. Sometimes you may get it, sometimes, okay. So this will be the structure dependence, okay. So in the coupling, okay, so as you can see here that when they are joined through the covalent bond and they are vicinal coupling to each other, vicinal, so you'll get the splitting, okay. If you have the long range, for example here, this is a 1 bond, 2 bond, 3 bond, 4 bond. So sometimes you may get the 4 bonds if, okay, if fulfill the condition, if there is an aromatics, if there is a cyclic, if the positions looks like the W, so you may get the W coupling or the long range coupling for the J4, okay. But nevertheless, okay, yeah, all this coupling will give the patterns in the proton NMR, the splitting pattern. So if you can analyze the splitting pattern, so these are the splitting pattern or the multiplicity by this coupling tree, or you can call it this coupling tree or the whatever diagram, whatever. Yeah. So this will allow you to detect the neighbor. So from the value of the J, so you try to look for another pair of the a group of the signal that have the same J, and then you can say that they are pair up. Okay. So this coupling tree, it can be very, very simple like this, simple. It can be complicated. Okay. So not everyone are able to analyze the coupling tree because sometimes is the result is spectrum is complex, especially if you have the overlapping peak. So this 1D multiplet analysis is powerful, okay, if you don't have any overlap, okay, all the signals are well separated, then it is perfect. But very often that we observe the spectrum with the overlapping. So it means that the 1D multiplicity analysis can be challenging. So as a result, people introduce 2D experiment. So because of the 2D experiment, you have another dimension that can simplify these informations. So we do not necessarily need to go to this the time-consuming steps, okay, especially in the multiplicity analysis. So the last information that you can obtain from the 1D is the intensity. So of course, I already mentioned that the area under the curve will be correspond to the atoms, okay, that contribute to the to this molecular level. So it means that if you're able to analyze the integral, so you know how many nuclei in this particular group, okay, per molecule. And if the sample is the mixture, yeah, so for the more advanced applications, so we also can measure the NMR sample with on the mixture. Okay, so for example, if you measure the plant extract or urine or any mixture, coffee or let's say the green tea extract. Okay, so you are getting the mixture. So the integral will give you the concentrations. Okay, if you relate it to the QNMR reference. Okay, so just take a look. Okay, so this is the proton NMR for this simple molecule called the ibuprofen. So first of all, when you want to compare, when you want to analyze, so we will try to count how many proton from the NMR. Okay, so this is the 0.96, so it can be round off to 1. So this is 1.9 is become 2. So we from the proton NMR, so we can get the round figure, okay, by rounding off the number, okay, at the bottom. Then we can total up how many proton, okay, here, yeah. So you get 18 proton. So in the proton NMR. So next, you would want to see, is it this number, is it consistent with the structure? Okay, this is called the ibuprofen. So you will start from the CH3, 3 proton, 3 proton, 3 proton. When you count, okay, this is a CH2, 2 proton. Okay, this is 1 proton, CH, and then you have another CH. So when you total up the proton from the structure, so you found that yes, they are tally. They are tally. So this, in this case, the number of proton that you observe in your proton NMR is consistent with the structure. So we do have the conditions that the proton NMR that you obtain is not equal to the total proton. If you have the structure than you expected, then the proton can be less. So this is the conditions where you, when you choose, this is due to the solvent that you choose. So very often that the this OH, NH can be disappear if you select the not correct, not appropriate solvent. So the OH, NH in NMR, we call their labile proton. So if you dissolve your sample in the protic solvent, for example, methanol, then this signal will be missing. So it means that when you try to analyze your proton NMR, when you try to compare, so you have to make sure that, okay, you are choosing the right solvent for your NMR sample. So if you wrongly select the solvent, so those signals may be missing because of the proton exchange. So in this case, they are exactly fit to each other. Okay, yeah. So we don't have the missing proton, we don't have the labile proton. The solvent is perfect. Okay. So this is another example. This is another slide to show the expansions. Okay, yeah. So means that this is a full spectrum, but I can cut these regions. Okay, so that I can have the better expansion. So this is from the MNOVA software. Yeah. Then we look at the carbon NMR. Carbon NMR is slightly different from the proton NMR. Why? The one main difference is in the carbon NMR. So when you look into the detail, so all the time that we obtain the carbon NMR as a routine, as a single peak, we don't see the multiplets, we don't see the coupling in the carbon NMR. So is it means that the coupling is missing in the carbon? The answer is no. Actually, there's a coupling shown in the carbon, but we purposely remove it. So why we want to remove the coupling? Okay, when you remove the coupling in the carbon NMR, it's called decoupling. Okay, we decouple the carbon. Okay, we decouple we perform the decoupling in the carbon experiment is because we want to make the carbon more sensitive. So you know that the carbon very often attached to the proton. So in the proton NMR, as already shown, the proton NMR able to detect the carbon satellite because of the J1 coupling. So this will be applicable to the carbon because carbon is attached to the proton as well. So carbon will detect the proton if they are bonded, single covalent bonded. But we purposely make this the proton disappear by perform a decoupling scheme so that we get the single peak per carbon resonance, so that we are getting the better sensitivity and less overlapping carbon result. Okay, so we have the reason why we want to perform the carbon decouple, proton decouple carbon experiment. Okay, so we are performing the proton decouple carbon experiment. So we make the proton disappear so that we get a single peak per carbon atom. So as similar to the proton, so when you do the carbon experiment and then we look at the result, so the carbon signal will also be spread along the chemical shift axis. So similar to the proton, the particular or specific regions can be referred or can be correspond to the specific functional group. Okay, so in the carbon experiment, okay, yeah, so we have the bigger window. Okay, as I already shown, we have the bigger window. So this number will be larger, okay, much larger compared to the proton. Proton is usually less than 15, less than 20, but for the carbon, it's usually more than 20, more than 100, very often, okay? So the window is larger, but every regions can be correspond to the specific functional group. So as shown here. Then the next step, okay, when you have the carbon and then you can compare with the table, the next step, okay, after you identify certain chemical shift group that belongs to the carbon. So the next step is we try to count, okay, the carbon signal in the experiment, and we try to count whether they tally with the molecule, okay? So here, from the molecule, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 carbon in the structure, okay? So how about in the carbon experiment? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have two signals very close to each other, okay? Two signals very close to each other. So this is the solvent. So we will ignore the solvent, NMR solvent. This is a deuterated solvent. So means that the number of the carbon in the experiments is not really tally with the structure. So this is common. Yeah. So we do have this type of the result, okay, that the number of carbon in the experiment is not tally with the structure. So the reason is there is a symmetry in the molecule. If there is a symmetrical plane that cross the molecule, the signal will be reduced, okay? So it means that if you have this type of result, then it means that you expect some signal or the carbon atom, they will give the same resonance frequency. Means that some of the signal, they are overlap, they are identical. So as a result, you have the less signal, okay, from the carbon, okay? Less signal from the carbon that you observe, okay? Supposed to be there, yeah. Then we go to the 2D, okay? Yeah, we go to the 2D. So in the 2D experiment, you have the x-axis and the y-axis. 2D experiment, you will observe a number of dots. So this number of dots, these are the dots that we call it cross peak, or you can call it correlation peak. So this is a very different from the 1D. 1D, you will see the peaks, okay? But in the 2D, x and the y, you will see the dots. So whether it's a x and the y is the same scale or not, okay? Yeah, this is another story. So in this case, they are different scale, okay? This is the between 0 to 10, this is between 0 to 100, okay? So this is a heteronuclear, but doesn't matter, yeah? As long as we have the two dimension, x and the y, and you see the dot, so these are the signal. So in the 2D, we will try to analyze all the dots that shown in the 2D plot. So if you still recall in the processing, yeah, we have the projection on the top, okay, and the projections on the left, okay. So these projections can be external projection or internal projection. So this external projection and internal projection is the additional display, okay. Yeah, it's not important to me, okay. So in the 2D experiment, what we are interested is the signal from these dots, signal from this dot. So these are the cross peak or the correlation peak. And how this analysis can be performed, even though you do not know NMR, if you know how to read the coordinate, you read the x coordinate, y coordinate, x coordinate, y coordinate, you are able to interpret the result. But in order to put it into the more sensible way or the more logical way, so you need some kind of a chemistry background, okay, or the molecular informations. Yeah. So the chemical shift or the coordinate in the 2D, okay, yeah, is the same, okay. Means that when you have the x and the y coordinate, so this is an x coordinate, this is a y coordinate. So this will be the chemical shift, okay. Chemical shift is similar to the 1D, okay, but the 2D, if you call the coordinate. So this coordinate or the chemical shift or the cross peak, how can we get this cross peak? This cross peak or the correlation peak is come from the neighborhood. So when you see neighborhood, so we have the many options, okay? You can have the proton neighborhood. You can have the proton-carbon neighborhood. You can have the close neighborhood. You can have the far neighborhood. So all these neighborhood, okay, able to give us the signal is because they are magnetic. they are bonded, they are covalently bonded, means that they are able to interact. So this is we call coupling, I already mentioned. So this cross peak in the 2D is the effect from the coupling. It can be the effect from the homonuclear coupling. It can be the effect from the heteronuclear coupling. So by looking at the 2D cross peak, we know the neighborhood, we know the coupling, so we know the structure. Okay, yeah. So from the spin-spin coupling, so we will try to analyze this based on the correlations, means that from how close these atoms separate from the bonds, okay, so from the covalent bond. So as I said, yeah, neighborhood, it can be the same neighborhood, it can be the different neighborhood. So it means that in the 2D experiment, we have many options, many experiments that we can perform. Depends on what information that you want to capture. If you want to capture the proton-carbon neighborhood, okay, so yeah, you can here, yeah, you can choose the 1-bond proton-carbon neighborhood, or the 2-bond proton-carbon neighborhood, or the 3-bond proton-carbon neighborhood. Or if you want to look for the proton-proton neighborhood, yeah, that is also okay. Okay, yeah. So it depends on what do you want. Okay, so all this, the basic is they are magnet. They are magnet. They are close through bonds. They able to interact. When they interact, they couple. They couple, so the 2D can be measured this coupling. Okay, yeah. So yeah, we take a look. Okay, yeah, we take as first example. You have the proton. Okay, that is the 1D, and you have the carbon for the same molecule. So if you want to know, yeah, how this proton and which proton is bonded to which carbon. Okay, now you have the first chemistry question. So if you have the proton NMR, you have the carbon-13 NMR, then you want to know which proton is bonded to which carbon. So if you still can recall in my previous slide, the proton bonded to carbon directly, so you can detect it as a satellite. So the signal is there in the proton, but very low, less than 1%. So this signal is not very useful if you have the overlap. So we have the special 2D that allow you to trace on the proton that is covalently bonded to the carbon-13, 1 bond. So this is an experiment that you can run in the 2D. And the information is exactly same as the satellite analysis, okay? Exactly the same as 1D. Just the 1D, very often you have the overlapping. And when you have the overlapping, this satellite signal may not be clear, okay? Because of the overlapping, you don't see this satellite, okay? Yeah, and if your sample is not very pure, the satellite signal will be mixed with the impurity. So we have the very special design experiments called the HSQC, that allow you to link, to join the proton to that carbon-13. So this is the 2D. So now you can see this is the overlay of the 2D, which with the dots here, and the 1D. Okay, yeah, you can call it as a projection, or in here I put it as a display overlay. Okay, so in the analysis, yeah. So now we are looking at the one of the experiment, the first 2D, called HSQC. Okay, HSQC is the 2D experiment proton carbon that allow us to link or to capture the signal from the J1 covalent bond. If you have the proton carbon, then you can use this HSQC 2D proton carbon to detect it. So when you look into the scale or the plot, the x-axis and the y-axis, they are different. So this is the heteronuclear. And the x-axis, or you call the F2, is the proton, always. This is always a proton. And then the y-axis, this is the F1. So this is a carbon. Okay, this is a carbon. So in this 2D HSQC, what we able to detect? We detect all the proton that is bonded to the carbon, J1. All the proton that is bonded to the carbon-13. So in this case, we are detecting the CH3, CH2, and CH. Okay, so if you have any proton that is bonded to the carbon, you're able to get all these signal in the plots as the coordinates. Okay? So it means that this you will not miss out any if you have the proton, okay, that is bonded to the carbon. So if you still can recall the depth experiment also work is a very similar way. You can detect the CH3, you can detect the CH, you can detect the CH2, okay? Yeah, so the depth and the HSQC is very similar, okay? But when you compare the sensitivity, the HSQC is more sensitive than the depth, okay, in general, yeah. So this is the one example. You see all the display all in the blue color, okay, blue color, okay. So this HSQC will detect the J1. So let us take a look, okay. So if you have this molecule, so you have the J1 here, J1 here, J1 here from the CH3, and then the J1 here from the CH2, J1 here from the CH. So this J1 all will be detect, proton-carbon correlations will be detect in the HSQC, because the HSQC proton-carbon is designed to detect the J1. So you have the signal from the CH3, signal from the CH3, signal from another CH3, and signal from the CH2, signal from the CH. So it depends on how many CH3, CH2, CH that you have, you will expect how many cross peak. If you have 5 group, then you have 5 cross peak. So I hope that this is clear. So this is the HSQC proton carbon, okay? So it is the single covalent bonded, and you're able to detect all the proton bearing carbon atom, okay? So all the signal will be captured. Next, okay? We go further a little bit. So take the same molecule, yeah, take the same molecule. So we know that you have the CH here, you have the CH here, you have the CH2 here, you have the CH2 here, and you have the CH3 here, okay? So you have the chemical shift, which is correspond to the proton, and the chemical shift that is correspond to the carbon that we're going to see now. So for the blue one, okay, the proton and the carbon that is covalently bonded, okay, single covalently bonded J1, okay, you have these dots. And then this will be the second proton carbon in the methyl, in the vinyl group, okay. And then you have these are the CH, okay, CH. Okay, so you see that this is the area under the curve, area under the curve. So can we detect, okay, the CH3, okay, yeah, the CH3 proton carbon, yeah. So as you can see here, the area under the curve is larger, okay. And when you read the coordinate X, coordinate Y, yeah, this is a coordinate X, coordinate Y, you get the chemical shift. You read the X and the Y, you get the coordinate, you get the chemical shift. And we know that this is the, how can we differentiate or distinguish between the CH and the CH3? How can we distinguish between the CH and the CH3? So the answer is very straightforward. So we can differentiate between the CH and the CH3 from the area under the curve, okay? If you have the area of the CH is 1, and then the CH3 is 3 times higher, okay? Now this is the, how can we differentiate between the CH and the CH3? And how can we differentiate between the CH2, okay? So based on the same argument, yeah, the CH2, the area will be 2 times, okay, compared to this 1, okay? So let us take a look, okay? So this pink color, the proton, which is the F2, and the carbon F1, if you read the coordinate, so you have this cross peak for this CH2. And then when you check the area under the curve, so this area is the 2 times compared to the blue and the orange. So with this, we know the CH2 from the area, okay, from the 1D area. And how about this group, which is the CH, the CH2, that the proton give the different chemical shift. So in the HSQC, so for this CH2, you will have 2 proton chemical shift, okay, 2 different X, but they are joined to the same Y, okay. You have the 2 different X, but they are joined to the same Y. So when you have this type of result, 2 different X that is the same Y, then you can say this is the same group. This is a CH2, okay. Just the area under the curve will be divided into 2 proton, into this proton, the red one and the purple one, okay. So you have the 1 proton each, okay. You have the 1 proton each, but when you total up, this is a CH2, okay. So you know that this is a CH2 because they have the same carbon chemical shift, but with the two different proton chemical shift. Okay. So in this case, the two proton chemical shift is the same. Okay. And you have only one carbon chemical shift. That is obvious. Okay. Yeah. So from the analysis, okay, yeah, from the analysis, so can we have some kind of the better or the edited version of the HSQC? Okay. So we will see that the we can read the coordinate x and the y. Okay. Yeah, you can see here this is the x coordinate, this is the y coordinate. When you read the x coordinate and the y coordinate, so you will know that the which proton is bonded to which carbon single bond. Okay. And then from the area under the curve, okay, for example, here this is one proton. So means that this is belong to one proton. Okay. And then this is one proton from the integral. This is belong to one proton. And I'm showing here, this is the blue color. Okay, blue color. Okay, this cross peak is the blue color. So I can, of course, I can plot it as black color. I can plot it as a purple, pink color, orange color, doesn't matter. But I just want to point out they have the certain color. Okay, certain color. Okay, certain color. Okay, so this is belongs to the CH from the integral. Okay, this is a CH. Okay, then continue. It's the same molecule, ibuprofen. So now the HSQC now looks slightly different. Okay, you have this orange color. Okay, so this color, if you check on the integral, this is the CH2. Okay, and this is the blue color. But then you check the integral, this is the 3 proton. So it means that this should be the CH3. Okay, so this is a CH2, this is a CH3. So we put everything together. So this is a special HSQC. We call the phase edited HSQC. So in this phase edited HSQC, you are not getting the same color anymore, but you are getting the different color. So if you still can recall, this is very similar to the DEP. Okay, the DEP 135 give you the CH3, CH, and the CH2 at the different phase. Different phase, you have the up and the down. So similar information can be obtained in the phase edited HSQC. Okay, and the HSQC is more sensitive compared to the DEPs. Okay, 135. So from this DEP experiment, no doubt we are detecting J1 because this is phase edited. You have extra informations on the multiplicity. So in the phase edited, similar to the DEP, it will give the CH and the CH3 same phase. So in this case, is the blue color. The CH2 in the red color. So it means that in this phase edited HSQC, so we have the more informations compared to the standard HSQC. Okay, yeah. So it means that from the result we can tell where is a CH2. Okay, CH2. Okay, J1 correlations. Yeah. And we look at the CH3, CH2, and CH. Okay, so the CH2 in this case, I plot it at the red. Okay, and the CH3 and the CH, I put it is blue. Okay, so that we can separate, we can differentiate between the CH2 from the CH and the CH3. Okay, so CH2 will be different color from the CH and the CH3. CH and CH3, they are the same color. Okay, they are the same color. So from the color, we cannot tell whether it's a CH or CH3, but from the integral, we can tell whether it's a CH and the CH3. Okay, so hope that this is clear. From the integral, we can tell whether it's a CH or the CH3. From the color, we cannot tell because they are the same. So we have another way to differentiate between the CH and the CH3 from the chemical shift. Okay, because we know that the chemical shift will give us the functional group. So the CH3 usually is the aliphatic chain. Usually the chemical shift is very specific. Okay. So now looking at this red and the blue, okay, so I have some few words that related to this. So as you can see here that I have the CH2, okay, this is a CH2, two proton from the integral, and I have this HSQC, which is a CH2, and they are red color, okay, red color, CH2. So I have now a group of signal, which is labeled as one proton here. This is another proton here, okay, one proton here, one proton here. So when you look at the HSQC, the one proton here, one proton here. So if you still can recall, the CH2 and the CH, they're supposed to have two different color, okay? Because the blue and the red, they coded the CH2 from the CH. So why this CH2, okay, and the CH, they are the same color, okay? So if the CH2 is different, they're able to give the different color from the CH. So this should be blue, okay? But why this is red? So just to recall, yeah, this is a CH2, yeah, from this group is a CH2. So we expect, okay, if this is a CH, then this should be the blue color. But they give us the red color. So because this is the anisotropic proton. So as I showed in the very beginning, so you may have two phenomenon. The CH2 may have the two proton chemical shift. So if they have two different proton chemical shift, in NMR, we say they are anisotropic. They are different. So that you have the two different chemical shift. So if they are the same, means that they're able to undergo free rotation. So they are isotropic. So the two chemical shift, proton chemical shift will be identical. So here, yeah, this is the two, this is a one CH2 and one proton from the methylene is here and another proton of the methylene is here. So in the HSQC phase editor, they will put it as the CH2, labeled as a red color. So this is, as you can see, that the HSQC actually is very useful. Okay, yeah, if you have this the anisotropic proton and the isotropic proton, you can easily differentiate from the phase edited HSQC. This is very powerful. Yeah, you can tell it easily. Yeah, from the HSQC plots. Then I will move on. Yeah, so this will be the some information related to the HSQC. Now I will move on to another 2D experiment called the 2D COSY. COSY stands for correlation spectroscopy. So in this correlation spectroscopy, you will observe from the result here, X and the Y, they are identical, as opposed to the HSQC, which is the heteronuclear. The first example, HSQC, is the heteronuclear, but this is the homonuclear. So when you look at this homonuclear experiment in general, any homonuclear, okay, not just COSY, any new homonuclear. So F1 and F2, they are identical, they are homonuclear. So you'll see very characteristic pattern. You can draw a line. So usually in the homonuclear 2D, we will display very often, classical way, we will display in the square. Okay, we will display in the square. So this square display allows us to draw a line from this point to this point. All the dots that fall along this line, we call it diagonal peak. So this is a diagonal line. So you have the diagonal peak. So this diagonal line or the diagonal peaks, these are the 1D. These are the 1D, okay? This is the 1D NMR result. So for the 2D analysis, we are not looking at the diagonal peak. We are checking on the cross peak or the off diagonal peak. So all this off diagonal peak means that either on the top or the bottom are the signal that we are interested. Okay, we are not interested at the peaks that fall along the diagonal line. Not important. Okay, for the 2D analysis, we are more focused on all the cross peak that fall above or below this diagonal line. They are the same. Okay, so it means that you analyze on the top or the bottom, doesn't matter. Okay, but they are the same. They are symmetric. They are identical. So these are we call the off diagonal peak or the cross peak. The cross peak tell us about the correlation. The cross peak will tell us about the correlation or the coupling. Okay, coupling. So from this off diagonal signal, so we know which proton they couple to another proton, which neighbor. Okay. So in the 2D COSY, okay, yeah, this is the 2D proton-proton COSY. So this experiment is specially designed to detect the proton-proton interactions that separate between 2 bonds, 3 bonds, sometimes 4 bonds away. So the 2 bonds we call the germinal coupling, 3 bonds vicinal coupling, and sometimes 4 bonds. Sometimes means that we are not necessarily detecting if the molecule adopt the special configuration or the special the linkage. Yeah. So we are able to detect the J2 is a mass. Okay, if you have the anisotropic proton as shown in the HSQC. So, and you can detect the J3, that is very interesting, okay, because it tells you the neighbor, this is the vicinal neighbor, and sometimes you may get the J4, okay. So just take a look, okay. So it's the same molecule again, yeah. So we know that this is the diagonal line. As I already said, the diagonal line, all the dots fall on this diagonal line. This is a 1D, okay. So you have the blue, orange, red, purple, the pink, purple, green. These are the 1D. So if you want to know the first one, the purple and the red, they interact, okay? When they interact, they couple. So we look for the purple and the red. So this purple and the red, of course, this is a CH2, okay? Yeah, this is a CH2. This is a methylene. You can get this information from the HSQC from the CH2, yeah? So of course, you can get this from the HSQC, but from the COSY, you get the similar information. So this J2 germinal coupling is not very useful for the structure building. It's just the additional information on top of the HSQC. It just confirm that you have the 2 protons that bonded to the same carbon. So it's a germinal information, okay? But it will show in the COSY if they are anisotropic, okay? If they are proton chemical shift, they are different. So they will show you the purple and the red, they interact, okay? They interact, they'll give you the cross peak as a J2. So next, we'll look at the blue and the orange. So when they interact, so first you need to check how many bonds, okay? So this 1 bond, 2 bond, 3 bonds. 3 bonds is possible, okay? 1 bond, 2 bond, 3 bond is possible. So the blue and the orange, because they are only separate by 3 bonds, so the blue and the orange, they're able to interact. So when they interact, it's a 3 bonds interactions, proton-proton. So we were able to capture this in the COSY, okay? Because the 3 bonds is near, okay? Near, okay? So the last group, okay, between the purple and the green. So you want to see whether if they couple. So if they're able to couple, it means that you're able to see the cross peak. And you count the bond, 1 bond, 2 bond, 3 bond. So if they are separate by 3 bonds away, so you're able to see the cross peak between the proton green and the pink. So they will give you the cross peak on top and the bottom. So this is again, okay, able to capture by the COSY. So the COSY will give you the information about the neighborhood, okay, neighborhood. So you see that instead of you looking at this 1D coupling, that you might have the overlapping, yeah, very often that you may have the overlapping. But when you see that when you analyze the COSY 2D proton-proton COSY, it's much simpler because the resolution is greatly improved because you have another dimension. Okay, yeah. So I hope that this is clear to you. The 2D proton-proton COSY able to capture the germinal coupling, and also the more important is the vicinal coupling. Sometimes you may get the J4. So if the molecule have the cyclic form, adopt the cyclic form, or the molecule, they have this functional group aromatic, or the shape looks like the W shape. So you may get the J4 in the COSY for these special types of molecule. Not every time you get this, but depends, okay? Yeah. So we look at the 2D proton-proton COSY in ibuprofen again, okay? So I will start from the 0.86, which is the methyl proton, which is here, okay? This is a methyl proton. Okay, this is the methyl proton. So we will have this 0.86, okay, which is here. So from the structure, we know that the, okay, yeah, it is there's a neighbor, okay, there's a neighbor, which is the directly bond, which is vicinal to this CH3, okay. So when you check the COSY, so from this 0.86, so we can move the line, okay, yeah, this is a way. So we will try to see from this and this, we will try to detect the signal, which is from this point to this point. So either you analyze on the top or at the bottom. So this, you get the second coordinates, which is the this is a 0.86. So you get the 1.82. Okay, so this is a 0.86, 1.82. So this is the coordinate that detect in the COSY. So anything in the COSY, any cross peak in the COSY give you the information about the vicinal neighborhood. Vicinal neighborhood. So we can say, oh, this vicinal neighborhood have the chemical shift of 1.82. So this chemical shift of the proton is 1.82. And they are close because you can detect in the COSY. If you count the bond, this is a CH3, 1 bond, 2 bond, 3 bonds. So they are separate by 3 covalent bonds. So that is true, okay? So we know that from the COSY, mainly detect J2, germinal, J3, confirm, J4 depends, okay? Yeah. So this is the COSY analysis, okay, for the ibuprofen. Then another fraction, another fragment. So from this CH, yeah, we know that this CH is also covalently bonded and adjacent to the CH2. So is it possible for us to detect the CH2, the chemical shift of the CH2? So from this 1.82 chemical shift, so we will go further to detect 1.82 left, right. Okay, doesn't matter. Yeah, so on the top or the bottom is the same, yeah, identical. So you get another chemical shift, which is the 2.42, 2.42. Okay, each side. Okay, doesn't matter. It's the same. So it means that with the COSY, so we can trace the third proton with the chemical shift 2.42. And when you check how far, so when you see from the COSY, this is a cross peak. So when you check from the structure, how far? So this is a 1 bond here, 2 bond here, 3 bond here. So actually this is J3. So J3 is a common, okay? Yeah, it's a standard correlations. So yeah, now you have the third neighborhood. So actually if you analyze the COSY, yeah, you will know the neighborhood. So rather than you look at the splitting pattern, you count the chemical shift, you count the coupling constant, okay, you check, okay. Sometimes, okay, it's useful, powerful, but yeah, if you have the overlapping, yeah, the COSY is the simpler way. Yeah, the 2D COSY, 2D proton COSY is the much simpler way. So then yeah, we try to see, yeah, from this 2.42, yeah, we can go further or not. So this 2.42, this is a chemical shift from the 2D cross peak COSY. So we're able to move to another signal, which is at the 7.10. Okay, this is a cross peak at 7.10. So it means that if you look at the structure, yeah, so that only point that allow you to trace this 7.10 is this particular proton, okay, or this particular proton from this change. So and from the chemical shift 7.10, it tells us this proton have to be somewhere in the aromatic or the carbon-carbon double bond, or more to the aromatic. So you have the aromatic proton. So this is the signal that link between this proton and this proton. If you count the bond, 1 bond, 2 bond, 3 bond, 4 bond. So actually this is the 4 covalent bond. Okay, 4 covalent bond. So this is a J4. So is it possible for us to detect the J4? The answer is yes, if they have this aromatic ring and they have this W shape, then you can detect the J4, but it's a weak signal. Okay, so is it possible for us to confirm this? Yes, we can consider the last experiment, which is the proton-carbon HMBC. Okay, yeah. So for the proton-proton COSY, we're able to detect the J2 coupling, which is a germinal coupling for sure. Okay, that is the additional information from the HSQC. Okay, so the J2 is the confirmed information that we get, okay, from the COSY. And more important for the COSY is to get the J3, okay, because with this J3 we can get the vicinal neighbor, so we can get the little bit bigger fragment, okay, vicinal neighbor. Okay, so vicinal proton J3, okay, allow us to detect the little bit further, which is adjacent proton, okay, adjacent proton. So with this COSY analysis, we can map up many fragment, okay, many fragment from one to another. So this is through the J3 analysis from the COSY. And if you're lucky, if the structure have the W shape or the cyclic, then probably you can detect the J4. Okay, so this will depend on the structure. So next, I will move on to the last 2D experiment for today's. So this is the 2D proton carbon HMBC. As shown here, the X and the Y, they are different. So this is a heteronuclear. So this is the very special experiment that's specially designed to detect, okay, the proton and the carbon. But now, instead of the single covalent bond as shown in the J1 HSQC, but they're able to detect remote neighborhood. Remote means that more than one. So typically we detect 2 and 3, okay, between the proton and the carbon. So you'll see, okay, how this result. So if you have the same molecule again, so in the 2D HMBC, if you record the 2D proton carbon HMBC, so we were able to detect the J2 from here, 1, 2, okay, 1, 2, okay, you have the cross peak here. So this is the 1, 2, 3, J3, okay. So this proton and this carbon, they are close through bonds. J2, J3, they will be detected. So similar, you have the J2, 1, 2, you have cross peak here. 1, 2, you have the cross peak. And then 1, 2, okay, you have the cross peak. And then 1, 2, you have the cross peak. And then 1, 2, 3, you have the cross peak. And then here, 1, okay, this is a 1, 2, you have the cross peak, okay. And then 1, 2, you have the cross peak. And then you have the 1, 2, and 3, you have the cross peak. And then 1, 2, 3, you have the cross peak. So all these 2 and the 3 will be captured in the HMBC. So when you try to analyze, you will see that a little bit complicated now, okay, because you have the J2 and the J3, okay, and you have many, okay, yeah, left, right, okay, yeah, you need to consider. So in the 2D HMBC, so what is the key informations? Okay, we detect the J2, yeah, we detect the J3 as the main standard signal. So sometimes you will get the J4, okay, but bear that in mind, you not always get the J4. J2, J3 is a must, okay. The J4 will depend if the structure, they adopt the planar structure, means that they are aromatic, so they have the pi electron, or whether they have this zigzag geometry, so you will detect the J4, okay. And more important information that we can obtain from the HMBC compared to the rest is this particular range of signal that is always related to the carbonyl group. So we will have the special signal that is related to the carbonyl group or any carbon signal that without any proton. So we call it the quaternary atom. So if you still can recall, the HSQC allow us to detect the CH3, CH2, and CH. But in the molecule, we also have sometimes the carbon without any proton. So the carbon without any proton, we call it quaternary. So it can be the carbonyl, it can be the ester, carboxylic acid, or aldehyde. So this carbon signal are missing in the HSQC. So we're able to detect this signal in the 2D proton carbon HMBC. That is very, very important. So from the COSY analysis, you may have all these fragments, but the HMBC allow you to detect the quaternary atom, quaternary carbon, and from this quaternary signal, we can join these pieces informations with the J2, J3, or sometimes J4 together. We can link them together. So similar from the proton carbon HSQC, proton COSY, you may come to the point you have many fragments. But in order to join them together, so you need to have this special point. Usually is the quaternary atoms, okay, that are missing in the HSQC. Definitely not appear in the COSY, okay. So you will appear in the HMBC. So with the J2, okay, this is the one J, and then J2 and the J3, okay, you can detect this linkage, and hopefully you can connect all this into the big molecule, into the molecule that you expected. So the J2, J3 is important to join the fragment, especially at the quaternary point, okay, quaternary point. So with this quaternary point, so hopefully we can build the structure, okay, and you get this structure later on, okay. So before I end up the second, this HMBC, just take a look. So I already color coded the proton chemical shift, okay, with this different color. And then we want to look for the 3 different carbon informations, which are the quaternary, okay. So it can be complicated to you, but make it simple. So let's say you have the first signal, okay, 178.38. So this horizontal line is the carbon chemical shift, okay. This because we are referring to the F1. This horizontal line 178.38 is a quaternary, and this horizontal line go through the purple and the red, okay. So I call it this is a red. So in the molecule, so you look for it. Where is the purple? So this is a purple, this is a purple, this is a red, this is a red. So the purple and the red. So in the HMBC, so just to recall, is detecting J2, J3 neighborhood. Neighborhood means that they have to be close neighborhood. So when you look for the purple and the red, okay, so the blue and the red, so which are close to these two, yeah. So I have this point, I can have this point. This is far from the blue, okay. We have this point at this point. If you look at this chemical shift, this is a very specific for the ketone aldehyde. So with this, I can easily identify, oh, this is the quaternary that is belongs to this, and that is confirmed, okay, because this is close to the blue and the red, okay, which is here. So similar at the second carbon chemical shift, okay, 172.64, which is labeled as the this is the red and the pink. Okay, we have 2 dots, red and the pink. So look for this. Red is here, the pink is here. Okay, the red is here, the pink is here. So which carbon is close to this red and the pink? Okay, yeah, it should be this. Okay, yeah. This one is close to this and then also close to this. Okay, so this 172.64, it should be this chemical shift. So the last one, yeah, I have the 2 purple, 2 blue, and 2 orange. Okay, and they are and the 2 gray. Okay, and they are linked, okay, to this 157.97. Okay, so I have the look for the this purple. Yeah, this is a purple. This is the orange is here, and the gray is here, and then the blue is here. So it means that close to all this. Okay, 1, 2, 3, 4. So which is the neighbor, closest neighbor? Okay, so this 157.97 is the either aromatic or the carbon-carbon double bond. So I have this. So with this, they are very near to this point. So it means that I can identify this without any error. Okay. So this is should be the signal that belongs to the 157.97. Okay. So in the analysis, of course, we can read the carbon chemical shift, proton chemical shift. Okay. Yeah. If you have this skill, we can read the X and the Y, and then we can identify. More important, we can use the HMBC to identify the quaternary signal, and we are able to we can identify it without any ambiguity. Okay, with this HMBC. Yeah. So another important HMBC informations that we can use is, okay, for example, in the ibuprofen, I have this molecule, and I run the HSQC, and I run the HMBC. Okay, I have the HSQC, which is a J1, and I have the HMBC, which mainly detect the J2, J3, sometimes J4. But when I overlay, okay, the HSQC and the HMBC, so this is one of the characteristic. Not every time you will see this, but if you see this, what it can tell you. If you overlay the HSQC and the HMBC together, and you see that these cross peaks, they are overlaid, okay? So this will give you the hints that there is the symmetry in the molecule. There is a symmetry in the molecule. And only when you have the symmetry in the molecule, we have the similar chemical shift. So when you overlay the HSQC with the HMBC, so they will have the overlay. Otherwise, you don't have this type of result in the regular display. Most of the time, they are different. So when they are overlay, means that they have the symmetry. So it means that this chemical shift and this chemical shift, they are identical. So this is 129.42, this is also 129.42. This is 7.1, this is also 7.1. So when they overlay, so they will give you the cross peak in the HMBC, which is overlay or identical to the HSQC. So before I finish, okay, different experiment, the 2D experiment, they come with a different sensitivity, okay? So some experiments are sensitive, some experiments are less sensitive. So in order to compensate the sensitivity, very often you are requested to put it more sample, okay? Yeah. So if the operator or the lab manager mentioned, okay, yeah, if you are running the 2D experiment, you need to have more sample, yeah? So this more sample is one option to compensate the NMR sensitivity. So another option is you can consider the different kind of the NMR probe. So the room temperature probe is the standard one. So of course, you can increase the sensitivity by using the liquid nitrogen to cool the coil to improve the sensitivity, or you can use the helium to cool the coil, okay, to improve the sensitivity. And another way to improve the sensitivity by applying the better higher field. So if you have the 400 megahertz in your system, in your university, then if you want to improve the sensitivity, then you can consider the 600 megahertz. So in UKM, you have 400 megahertz system, you have 600 megahertz system. So it depends on your sample. If you have the limited sample, then you can use the 600 megahertz to measure your sample to improve the sensitivity. Yeah. So Brooker, we also have a number of training, NMR training, that you can join on demand. Okay, yeah. So once you get this PowerPoint, you can click on this page. So it will lead you to our web page. So you can register if you wish. Okay, yeah. We have the NMR training start from 2020 because of the pandemic. So we collect a number of NMR training for the customer. So you can join and then you can get the free certificate as well. Yeah. So with that, I finish up my presentation today. And thank you very much for your attention. Then we open for the question and answer.
Thank you very much, Dr. K, for your presentation. Very detailed. I think everyone could benefit with this webinar session shared by Dr. K from Brooker. So before that, I would like to make announcement to all participants. Kindly please fill in the survey form. The post already, the CRIM, you can post already. Put it in the chat box. I mean the link. Kindly please click on the link and fill in the Google form. And also, Dr. K, we have actually several questions from the same person, which is Rauda. But she asked quite a lot of questions.
Okay.
Actually,
so I can look into the chat and then I answer that. So
yes.
Maybe
you can select which one.
Yeah, sure. Yeah. So the first question, one question is, can we remove the signal of the solvent used if they dominate the spectrum? Yeah, the answer is yes. So we can remove through the acquisition. Okay. So it means that if you have the spectrum, then you cannot change anything. But if your sample is still in the magnet, so you can remove through the water suppression scheme. So there is an NMR experiment that allow you to reduce the water signal. Yeah. So this will be go through some kind of irradiation, and then the water signal or the solvent signal in general will be reduced. Yeah. So the answer is yes. but not through the processing. Yeah, it's not possible. Yeah, yeah. From the top spin, it's not possible. Yeah, so the frequency selections play an important role in the quality. Okay, so this frequency selections, actually, we do. I'm not the question is not very clear to me. But if you wish to measure the NMR experiment on the particular nuclide, okay, means that let's say hydrogen elements or hydrogen nuclide, then you just need to put in the sample into the magnet, and then you just need to do the ATMA. So it will tune the frequency to the nuclide that you want to observe. For example, the proton. So if your sample contain the fluorine, so you can also put the sample in, and then you do the ATMA, okay, at the fluorine frequency. Yeah. So this is the I hope that I interpret it correctly. So the frequency selection. So if instead this frequency selection is a step, a must step if you want to observe a particular nuclide. For example, fluorine 19 or the silicon, okay, yeah, 29, yeah, or the carbon 13 or the nitrogen 15. Yeah. So you can do the ATMA. So the machine will tune according to your sample to the frequency that you are interested. Yeah. Okay. Is it possible to use the temperature to dissolve the sample before you run? The answer is yes, but you need to make sure that your sample is not recrystalline or solidified when the sample is sitting inside the magnet. So it means that you can heat up the sample to dissolve it, okay? And if the sample is not really dissolved at the room temperature, so you can ask the NMR lab manager to increase the probe temperature. Yeah. So in the NMR instrument, so you can adjust the temperature to higher temperature so that your sample is remain in the solution form, okay, or the soluble way. Yeah, yeah, solution form. Yeah. So how can the NMR benefit us to know the percentage of the epoxy content before and after the synthesis product? Okay, so this is more to the quantification. Okay, so in order to answer this, so first of all, you need to know the where is the epoxy signal from the NMR spectrum. Okay, so you need to identify the signal chemical shift, okay, that is related to the epoxy, and then before and after the synthesis, you can measure the sample, okay, and then you compare the NMR result. From the chemical shift, if they undergo some kind of epoxidations, so you will see this signal growing, okay, and then from the integral, so you know how much, okay, percent, okay, has been converted, okay. So it means that first you need to know at least where is the signal for the epoxy with the epoxy group, okay, and where is and then you need to run the blank. It means that before the epoxy, before the reaction, you need to run one, and then after the reaction you can run one. Then you can compare from the chemical shift the location, and from the integral, so you can tell how much, okay. So if you want to tell more exactly how much the content, then of course you can add in you can consider the qNMR, so which is the quantitative NMR. So you can compare with the known concentrations from the one chemical, and you can calibrate this, and based on these calibrations, and you can calculate how many percent, okay, have been converted, and that is possible. Yeah, but you need to know where is the signal at the first step. Yeah. Can lithium NMR predict how much lithium ions connected to the O and the C? So this is the very specific questions. Okay, so we do have the we do have the NMR applications that related to the lithium. Yeah. So the how much lithium ion? So that is related to the quantifications. Okay. Yeah. So so for these questions, can you write me the email, and then I can reply you in person. Yeah. So this is very specific. Okay. So the cis and the trans. Okay. Yeah. So again, this is a very good questions. Yeah. Of course, we can tell from the NMR the cis and the trans two-way. Okay. Yeah. But the more precise way is through the coupling constant. Okay, the two-way one is from the cozy 2D cross-fit. Okay, so the cis is the vicinal. Okay, the trans is also the vicinal. So you will see the coupling coupling information, the JA3 in the cozy. Okay, but to tell the exactly the cis and the trans, so you only can see from the coupling constant. So the trans of the configurations will lead to the larger coupling constant compared to the cis. So usually the trans coupling constant is about 12, sometimes 13 hertz. Okay, yeah. So the cis sometimes is about less than 10 hertz. So if you measure the distance between the peaks, okay, then you can tell whether it's a cis or the trans. So yeah, two-way. Okay, one is from the cozy, or more precisely from the 1D proton multiplets. Okay, yeah. So okay, so is it possible to monitor the polymerizations conversions? So if you have the, I'm not sure. Are you referring to the monomers? Okay, the conversion. Okay, conversion rate actually is possible. So we do have some documentation on to calculate the polymerizations percent. Okay, yeah. So by comparing a certain range compared to the another range, so we know how much the conversions or the polymerizations have been take place. Yeah. So that is possible. I'm not sure whether it's the result is on the proton or not, but either is on the proton or the carbons that it can be tell. Okay, yeah, as the polymerization take place, so some of the signal may be reduced and some of the signal may be grow up. Okay, so that is possible for the proton, and I think it's also possible for the carbon. Okay, yeah, I hope that this is clear. So for the questions that I'm not able to answer by verbally, so maybe you can drop me an email and I can reply you. Okay, yeah. So to get two singlets, but I got a doublets. I'm supposed to get two singlets. Okay. So it's if the two singlets are close, yeah, so you may get the doublets. Okay, so the resolution, yeah, this is because of the resolutions. Yeah, so because the signal are too close in the chemical shift, so they're not very well resolved. Yeah, but you can tell easily from the HSQC, very easy. Okay, if you run the HSQC and then you have the two different carbon chemical shift, then these are the two different group. Okay, yeah. So yeah, this is very common in the metabolomics. Okay, when you have two singlets, yeah, not necessarily they are singlet. Okay, yeah, they can be the two when you see a singlet, not necessarily they are pure. Okay, so it means that when you run the 2D HSQC, then if they really only have one cross peak, it means that they are pure. Okay, yeah. So the solubility, it could be the solubility that caused the problem. So or sometimes we call the viscosity. Okay, so if the solvent is the very viscous, for example, you've measured in the DMS, so you may improve the resolutions by increase the temperature. Yeah. Okay, so I think yeah.
Okay, Dr.
most of the questions.
Is it I think if participants have further question, I think you can email to either to Dr. Tay or just email to the organizer, then they will forward the question to Dr. Tay. Since we already past 12, so again, thank you very much, Dr. Tay, for very invaluable, and I think everyone having new knowledge with the latest, features from the top, Broker, for example, the application for the NMR. So this is very good for us. When we would like to elucidate the compounds, because NMR, I think it's more like you solve the jigsaw puzzle, and especially when with the 2D NMR, you will get a lot of information that will help you in terms of elucidating the compounds. Before we end this webinar, may I ask everyone to switch on your camera so that the host can take our photos. Maybe the technical can give instruction to us. Okay, ready? So technical ready to take our photos? I will count 1, 2, 3, okay? 1, 2, 3, smile. And again for the next slides. 1, 2, 3, smile. Again, because we have about 100 participants. 1, 2, 3, smile. All right, okay. With this, I would like to end our webinar. Again, thank you very much, Dr. Tay, for your time, for your sharing session and everything that you shared to us today. We hope to see you again for the next webinar with Brooker, hopefully in the future. And to all participants, thank you very much for your time. And hopefully we can meet again for the next session. And that's all for me. Stay safe and bye-bye. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, everyone. Thank you, Dr. Tay. Bye-bye.
Thank you.
Bye.
Bye.
Please, Ma, can we have the email address of the presenter? I don't have the email address. I want to ask some questions maybe later.
Organizer will share the email in the chat.
Yep, later. Thank you.
Okay, thank you very much.